Good evening, all. Welcome to the session Aero and Aquatic Vehicles 1. I am Professor Milena Pinto from Cefet Rio de Janeiro, and I will be the chair of the session. It's a pleasure to be here. Thank you. So the interaction in the section will happen the following way. If the authors want to present in an online fashion his or her presentation, he will be welcome. But if he wants to show the video, display the video of that he or she recorded, the host can do it. And then the authors will come again to answer the question raised by the audience. So I hope this interaction can be successfully done. And I wish the authors good luck with the presentations, and I wish a really good session and conference to all of you. So the first paper from this session is entitled Tracking Nonlinear Model Predictive Control for Obstacle Avoidance. It's from Marcelo of Federal University of Minas Gerais. So I will ask the host to play the video.
Yes, please. Thank you. Hi, I am Marcelo, and I will be presenting the work entitled Tracking Nonlinear Model Predictive Control for Obstacle Avoidance, made in collaboration with Antonio Ferramosca from the Bergamo University, Italy, and Guilherme Raffo from UFMG. So the introduction. Systems able to perform autonomous navigation are expected to play an important role in the upcoming years in the most distant types of application. As example, we have autonomous car, unmanned air vehicles, and unmanned underwater vehicles. The interest in this type of system is related to their ability to execute tasks with enhanced security, reliability, and performance. An important feature of autonomous motion system is their ability to navigate safely while handling unexpected situations. In this work, we are particularly interested in the problems of path planning and control, mostly on how they can be performed together. We divide the solutions of path planning and control into two groups. The multi-layer approach, it is well established and with good results in real commercial applications. However, under some conditions, it might present performance deterioration and suboptimal responses. The single-layer approach, on the other hand, has an arduous design process due to its complexity. It requires a compromise between planning and control, since it is a multi-objective problem. However, it may have the benefits of avoiding suboptimality. Optimal control, it is an interesting idea to work with on the coupled scheme because it allows gathering distinct objectives together and to handle explicitly constraints. Particularly, we are interested in model predictive control, a finite horizon optimal controller, because it provides firm guarantees of stability and convergence from the control algorithm standpoint. Besides, its prediction-based nature allows better tracking performance with smoother control signals. One of the problems that we are mostly interested in this work is the loss of feasibility during navigation. We can see two main sources of feasibility issues, the system on dynamics limitations to perform a given task, and the limits and obstructions in the workspace. In the literature, single-layer optimal controllers for avoidance are designed considering obstacles either as hard constraints or soft constraints. When considering them as hard constraints, feasibility issues could occur due to a large number of unknown pop-up obstacles, since the search space of the optimization problem might become excessively small. On the other hand, considering soft constraints, the idea followed in this work, feasibility problems might occur due to changing targets, common in this type of application, and due to a significant deviation required to avoid an obstacle because this might drive the system outside the controller's domain of attraction. Among the MC formulations, tracking MC is particularly interesting for the problem because it has the advantage of recursive feasibility for any changing reference. And it provides a controlled system with large domain of attraction when compared to stabilized MPC approaches. The central idea of the strategy is the use of an artificial variable to be a new feasible reference for the controller. And with an offset cost function, we intend over time to minimize the distance between the artificial variable and the output target, if feasible. If not feasible, the controller will drive the system to the equilibrium point closest to the target. Thus, considering the tracking MPC approach and the control problem with obstacle avoidance feature, the contribution of this work are the extension of the tracking MPC framework to include avoidance of some specific regions in the output space, a new single-layer nonlinear control scheme for planning and control, either kinematic or dynamic, and solution to feasibility issues of some of the soft constraints-based MPC approaches found in the literature. The problem statement is design a controller able to drive safely the motion system towards a goal by means of an artificial reference point obtained to avoid obstacles. For that, consider this constrained nonlinear discrete time system, where typically y represents the motion system position, allowing the obstacle avoidance to be handled in the Euclidean space. However, there is no constraint about how the states and outputs could be defined. Here, we assume that the system is locally controllable and that the states are available. Also, the constraint sets are compact with the origin inside them. The optimal control problem is represented by this optimization problem that aims to minimize a value function using the following decision variables: the sequence of predicted states, the under arrow, x, the sequence of predicted inputs, the u with the under arrow, artificial states, xa, inputs ua, and outputs ya. The prediction horizon is equal to n, and in this problem, the first constraint is an initial condition constraint. The second one subjects the prediction process to the motion system dynamics. The third and the fourth enforce the system constraints to the state, input, artificial state, and artificial input. The fifth and the sixth ensures that the artificial variables are an equilibrium condition for the system. And finally, the last constraint is a relaxed terminal equality constraint for stability reasons. Note that the desired reference does not appear in the constraint, which solves any recursive feasibility issues. Following the MPC receding policy, at each sampling time, the first element of the control sequence is applied to the system, the horizon is receded, the initial conditions are updated, and the optimization problem is solved again. The value function for the problem is composed by a stabilized stage cost, standard in MPC, an offset cost function to make the artificial output converge to the desired output, and an avoidance cost to drive the artificial output away from the obstacle. It is worth noticing that the system is controlled with respect to artificial variables and not the user's desired ones, bringing feasibility assurance to the problem and enlarge the domain of abstraction. Also, note that the number of obstacles is unknown and not limited. However, to simplify the notation, a summation of the number of obstacles is omitted here. The assumption of stabilized cost is that it is a continuous, convex, and positive defined function that is zero at zero. The assumption of the offset cost is that it is a continuous, convex, and positive defined function that is zero at zero. Additionally, and most important, this function is strictly increasing with respect to the distance between the artificial output and the desired output. Finally, the assumption on the avoidance cost is that it is continuous and not increasing with respect to the distance between the artificial output and the obstacle position for all the obstacles. Also, this function is superiorly bounded, and it goes to zero when the distance is greater than gamma. These assumptions and the controller formulation and any function respecting them might be considered. Now let's see some examples of how to set up this controller. The stabilized stage cost can be a quadratic cost penalize the state error and the control effort, as common in MPC controllers. The offset cost function can be also a quadratic cost penalize the artificial reference and the target. And the avoid cost function can be some S-shaped functions such as sigmoids in hyperbolic tension. For instance, here we are using a logistic function. Some important remarks. The offset and the avoidance cost form an artificial potential field, but the avoidance cost must be bound. The controlled system may suffer from local minima depending on how the offset and the avoidance costs are selected. If a local minimum appears, the controller will stabilize the system at the closest equilibrium point. It is worth to say, however, that choices with global properties might be made, for instance, something like the harmonic fields. The offset and the avoidance costs compete against each other, in a way that collision might occur since the avoidance cost is bounded and the offset cost is not. Thus, it is necessary to work with bounded workspaces, aiming to know the worst case of the offset error to properly choose the avoidance parameters. Finally, large horizons in slow dynamic systems should be avoided because it might make the artificial reference to jump a whole obstacle. If this happens, collision might occur. So to analyze the proposed controller behavior, let's consider quadrilateral review with 6 degrees of freedom and 4 actuators actuated on lifted forces. Thus, the generalized coordinates for the system is composed by the translation and rotational variables. And to model the system use the Euler Lagrange formulation, three coordinate frames are defined: the inertial one, the body frame, and the center of mass frame. Since we are considering a whole body control problem and that the system is underactuated, we consider the thrusters tilted towards B by a fixed angle alpha to increase the system controllability. Besides, the center of mass is placed from the center of rotation. Thus, the coupling between translational and rotational dynamics is represented in the model. For control design purposes, the nonlinear model disregards the center of mass displacement. However, the system is simulated with the displacement. Thus, in the simulation, modeling uncertainties are considered, aiming to be more realistic. The UAV workspace is limited and obstructed by 9 and no obstacles. A 3D LiDAR-like sensor is emulated with a spherical range of detection of 3 meters. The sampling period is 10 milliseconds. The horizon is equal to 50. And just to give you order of magnitude, key is around 0.1, R is around 2, the offset gain is around 1,000, and the avoidance gain is around 50,000. The thrusters lift forces are constrained by 12 newtons, and the states are also constrained. Finally, the simulations are performed using MATLAB and the Casage toolbox with the IP OPT solver. In the video of the simulation, the system must go towards the black dot behind the obstacles. The red dots over the obstacles represents the obstacle position considered, and we can see on the right animation the level curves for the offset and the avoidance cost. And here we can see how they change the presence of the obstacles. We can see also that the controller in the simulation avoids the obstacles with success. Notice that if avoidance feature wasn't present, the obvious and less energetic cost path towards the goal would be a straight line, which would lead to collisions. Here we can see the whole trajectory performed by the UAV, while on the right side we can see the tracking error. It is interesting to note that the control algorithm gives up performance to achieve safe navigation, which can be seen where the error stops decreasing at some points before converging to zero. Here we can see the orientation and the lift forces. Because we are using a nonlinear controller, we can actually perform yaw maneuvers without cascading the controllers. Besides, all the angles stably converge to an equilibrium orientation, which occurs since at the end of the execution, the UAV must be hovering. The lift forces on the right figure shows that the controller was able to perform the tracking without overpass the actuator saturation limits. So the conclusions. In this work, a novel unified non-decoupled framework to handle dynamic control and planning at the same time was achieved by means of the artificial variables and the obstacle avoidance cost added into the optimal control problem. Here, we have extended the tracking ABC formulation to avoid some regions of the output space. We have carefully avoided in the design process any ingredient that could bring feasibility issues to the problem, and we avoid suboptimal responses by considering a single layer solution. In future works, formal analysis of asymptotic stability, optimality, and recursive feasibility will be provided. We also want to exploit some ideas for global solutions. And finally, we want to evaluate the controller in real experiments with UAVs or non-autonomic mobile robots. Thank you for the attention.
Thank you very much, Marcelo. Congratulations to your work. It's really interesting. I don't know if we have questions from the audience. Let me see. I don't know if we have questions on YouTube channel.
Yeah, there's no question on the YouTube.
Okay. Okay, so so Marcelo, I will. You asked to do the questions in Portuguese, so I will start doing this question in English. if there's no problem, just to make
No,
all the
there's no
audience
problem. We
understand.
can do. Yeah,
Okay,
we can do in
okay,
English,
thank you.
of course.
So first of all, congratulations once again. It's a really interesting subject and work. So I think the idea of integrating control and planning strategy in one single optimal control problem is really nice. So congratulations. And I was wondering if you compare your strategy actually with another in the literature.
Yeah, I didn't actually, I mean, compare because the yeah, I should have compared, but the thing is, to be fair, I need to compare with empathy controllers, right? And the good comparison would be, for example, use the empathy controllers I use, for example, hard constraints to represent the object. And I didn't did this, but I know that some problems might occur in the formulation of hard constraints. For example, if we assume an absurd scenario where we have the UAV inside the closed room and the reference outside this room, and the reference keeps going far away, the UAV will stabilize. In our approach, the UAV will keep hovering on the position because the reference is unfeasible. So this type of things I know that will occur, but it will actually be interesting to compare in a similar scenario.
Yeah, no, for sure, for sure. Just by curiosity, okay, you perform your results in numerical simulation, right? MATLAB software. So do you intend to exploit the results in some realistic software like Gazebo, ROS?
Yeah, for sure. The resulting simulation, it is a multi-parametric optimization problem. So we expected to find some explicit solution for this. And I'm saying that because nonlinear MPC are costly computation.
Yeah.
So we still need to reduce the computational time to run real experiments. And yeah, we have a good simulator in our research group to test with in a more realistic scenario using hard in the loop, for example, asynchronous hard in the loop. And we intend to do this in the future.
Okay, nice. Just the final question, I promise you, okay? Just
Okay.
by curiosity again, I read in the conclusions and feature work actually that you intend to deal with local minimum problem.
Yeah.
So
yeah, because
can you
I mean,
explain how can you do this?
Yes. I mean, the first thing is I'm not making an assumption. I'm making some assumptions about the offset class function, the avoidance class function. So the thing is, can I choose an offset class function and an avoidance class function that actually leads to global solution if it respect our assumptions? Because we have some recent results showing that this control is actually asymptotically stable. So we were looking into, for example, the ideas of harmonic fields because it presents some global solutions, for example, and also we can look into some ideas of having the parameters of the controllers time varying because it's not a problem for the formulation, the point of view of feasibility and stock stability, and we could solve this type of problem of local minimum. So we are trying to do this type of.
Okay, this is already undergoing work?
Yeah, it's undergoing research. Yeah.
Okay, Marcelo, I love your work. I would like to talk more, but I will proceed with the next work. Okay.
It will be a pleasure to talk to you later. Thank you.
Okay, thank you very much, Marcelo. So moving to the next paper, we have the work entitled Unmanned Aerial Vehicle with Hybrid Lift and Propulsion. This work is presented by Alison. So I will ask the host to display the video from Alison.
Okay. Dear participants, In this work, an unmanned aerial vehicle with hybrid elevation and propulsion will be presented. This work is authored by me, Raimundo Freire Jr., and Luiz Gonçalves. Two categories of UAVs are well defined: fixed-wing and multi-rotor. Our work consists of these two categories, creating a double hybrid UAV, capable of generating lift by the wing and also by the multi-rotor, and by electric motorization and combustion. The multi-rotor used for vertical takeoff and landing is composed of a set of propellers with electric motors, coupled to structures with three arms. This structure generates less drags compared to other models with more arms. For horizontal flight, we chose the flight-wing model, due to its ability to generate lift in almost its entire structure, and additional to not recurrent impingement, which increases the drag coefficient. The basic flight functions intended with this hybrid UAV concept are: and at first moment A, the UAV hybrid is landed with the combustion engine at idle speed. At instant B, the UAV hybrid activates the powertrain of the multirotor and takes off vertically. At time C, after reaching the necessary altitude, the hybrid UAV performs a transition to horizontal flying. At that moment, the multirotor powertrains are returned off and the thrust is generated by the combustion powertrain. During the mission, it is possible for the hybrid UAV to perform slow or hover flying, decelerating the combustion powertrain to idle and activating the multirotor electrical powertrains if necessary. Thus, as we can see at instant D, the hybrid UAV can be used to analyze some specific target. Then the UAV returns to horizontal flight in in-play mode at instant E. The UAV starts the vertical land procedure at the moment F, activating the multirotor powertrain and decelerating the combustion engine to idle speed, and the mission ends at moment G, when the hybrid UAV is landed, again on the ground. The multi-rotor system used coaxial motors with counter-rotating propellers. They set promoters up, down, clockwise and counterclockwise movements, forwards and backwards movements, as well as right and left movements. One of the important points in this work was to coincide the center of gravity of the flywing with the multirotor, reducing the need for corrections by the control board during the multirotor flying. The multirotor has a radius of 0.51 meters from the center of gravity. The flywing has wingspan of 1.5 meters with an area of 0.53 square meters. The positive deflection flywing concept requires higher speed than a conventional aircraft for the control surface to act efficiently, ensure control and good maneuverability. To meet this requirement, three semi-symmetric profiles are analyzed: the ZAG-12, the MH-145, and CPQ-1.7. The choice and use of one of these profiles in the construction of the flywings is due to slow moment coefficient values, since the aircraft will not have an empennage. We analyzed the three profiles using the Profile 2.2a software, comparatively as function of the angle of attack for the characteristics curve of lift coefficient and drag coefficient. In the analysis, we considered as input data a cruising speed of 13.8 meters per second and a radians number of 270. Considering that UAVs are not aerobatic aircraft, the flight must be performed with the longitudinal wings aligned with the horizon. We considered values between 5 degrees negative and 5 degrees positive for the analysis. Thus, analyzing the lift coefficient graph, the profile that presents the best performance is the ZAG-12. This profile also has the best performance for drag coefficients from 1 degrees negative to 5 degrees positive. It is also the easiest to make due to its great thickness. Our system architecture is divided into 4 subsystems. The blue part is responsible for controlling and stabilizing the multi-rotor. It is commanded by APM Model 2.8 control board. The subsystem is green is responsible for controlling and stabilizing the flight wing. It controls the elevation servers and the combustion engine throttle server. An APM Model 2.5 controller board is responsible for commanding the system. The subsystem in red is the power supply, consisting of the lithium polymer battery, with a voltage 18.5 with capacity 5000 mAh. The orange subsystem is responsible for remote control of the UAV hybrid. This control and stabilization system architecture using 2 autopilot modules is configured to work alternately. With one subsystem active, the other remains at rest. The activation of each subsystem is done by means of the 3-position switch on the transmit radio control. Before developing the UAV hybrid, we analyzed each flight subsystem separately. The first prototype manufactured was a fly-wing with a wingspan of 1.2 meters using an electric motor. The objective was to understand the behavior of the fly-wing in flight. We tested 2 configurations activated remotely through the radio control. In the first configuration, the control board performed automatic stabilization during the flight. In the second configuration, there was no assistance. During the flight with stabilization, after some adjustment, the flywing behaved perfectly controllable, responding to all commands and without stabilization. The flywing was completely unstable. The second prototype was a multi-rotor with 3 arms. The main objective was to verify the stability and correction capacity of the control board during the flight, and also the responses to remote commands. We performed several tests, always with the stabilization mode activated. The control board was able to act on the corrections of disturbations caused by wind in real time. The responses to the commands proved to be totally efficient, having been performed several flights. We also verified the average flight time autonomy, which is 12 minutes. After the development of preliminary prototypes, the final prototype was manufactured. According to the concept presented, this prototype uses a combustion engine for horizontal flight. The wing structure uses polystyrene foam, reinforced with fiberglass rods. A central structure was made of plywood, and the multi-rotor support uses a tubular aluminum profile. We carried outdoor tests using only the multi-rotor, with the combustion engine turned off. The second series of tests has been carried out only with the fly-wing configuration, with the multi-rotor mode turned off. Stabilization mode via the control board was always activated. The controls responded perfectly. Only basic maneuvers were performed. We made the final test with head-on wind including vertical takeoff and transition to horizontal flight. The combustion engine remains at idle until the aircraft reaches approximately 4 meters in altitude. We started the acceleration of the combustion engine and deceleration of the electric motors. The hybrid UAV performed this transition perfectly, initiating horizontal flying supported by wing lift. We introduced a new architectural design of the hybrid UAV with a sample configuration. Experiments and the results show versatility of the UAV operating in the field. We performed several tests, including takeoff, horizontal flight, and transition tests successfully. Our final UAV has proven to be functional and the hybrid system effective. Our work is under patent process. Future work includes more field tests to improve. Thank you very much.
Thank you, Alison, for your work. I will start in English, then in Portuguese, okay?
Ok, português, por favor.
Okay, so first of all, congratulations. This is really interesting work. As far as understood, you have a hybrid UAV that has a combustion train powertrain set along with electrical motors, and you can land and lift vertically, and then you can switch from electrical to combustion powertrain. So compared to the literature, how is the performance? Vou traduzir agora, Alisson. Então, assim, eu achei bem interessante o seu trabalho. Você tem essa mistura, né, de se eu utilizar esse... nem sei como é que fala traduzido, né, mas seria a parte de combustão com a parte dos motores elétricos, né? Você chegou a fazer uma comparação com a performance de utilizar esse VTOL, né, que faz esse pouso e a subida de modo vertical, mais essa mudança de combustão com a parte elétrica?
Opa, boa tarde, obrigado.
Boa tarde, eu nem falei boa tarde,
Não,
desculpa.
tranquilo. Obrigado aí pelo seu apoio. Viu? Assim, em termos de tempo de voo, a gente vai ter uma diferença bem grande, né? Enquanto a gente tem aí uns 15 minutos de voo no multirotor com a bateria, na parte de combustão a gente vai ter aí o quanto a aeronave tiver capacidade de carregar. Hoje ela está com um tanque de mais ou menos 250 ml e aí já vai dar em torno de 27 minutos, mas você vai poder aumentar aí até acho que uns 750 ml, entendeu? E aí vai depender também do tempo, né? Quanto mais ventos, menor vai ser o tempo de utilização do motor a combustão. Ele vai acelerando, vai consumindo mais. Mas a diferença é bem grande quando a gente compara com baterias, né? E conforme ela vai consumindo, a aeronave vai consumindo combustível, né? A gente usa metanol, você vai aumentando, vai diminuindo o peso e ela vai aumentando a capacidade de tempo de voo também, vai melhorando a performance.
Perfeito. É difícil, né, fazer uma comparação, né? Você tem que fazer uma comparação quase qualitativa mesmo, né?
Isso, é um pouquinho complicado. E assim, os testes de bancadas, eles dão uma diferençazinha bem grande quando a gente coloca para fazer os testes externos, né? Principalmente dias de muito vento. Mas a diferença é bem grande. A gente consegue alcançar distâncias que não conseguiria só com multirotor. Em compensação, você consegue fazer o pouso e decolagem vertical que você não consegue com a asa, né? Só com a asa. Então, a ideia é utilizar essa junção aí para pegar o melhor de cada um projeto e conseguir, né, juntar tudo e fazer uma aeronave diferente.
Não, bem interessante. E você fala que ele caiu, né? E aí você
Caiu.
acabou mudando a configuração. Só que você não menciona qual foi a configuração que você mudou para fazer ele funcionar depois. Você fala um pouquinho para gente?
Assim, quando tivemos a queda, os logs da placa controladora eles se perderam, né? Então ficou um pouco obscuro analisar o problema da queda. Mas analisando os vídeos e alguma coisa que a gente conseguiu buscar, por algum motivo ela acionou o multirotor durante o voo, que era para ser só da asa voadora. Então ela deu um giro e caiu. Só refizemos todas as configurações do código, de cada código, a gente está usando uma placa controladora para cada tipo, né, de voo, e não tivemos mais um problema. Então, assim, ficou um pouquinho obscuro o problema que aconteceu, porque os logs foram perdidos na queda.
Ah, perfeito. Alisson, cara, eu gostei muito do seu trabalho. Assim, bem interessante mesmo. Parabéns. Muito obrigado pela participação.
Eu que agradeço, mais uma vez.
So thank you very much, Alisson. And we are moving to the third paper of the session entitled Trajectory Detection Method for Transmission Line Path Following Control. This work is presented by Guilherme, and Guilherme wants to share his screen to present his slides. Guilherme, you can share.
Okay. Can you see my
Yes,
screen?
yes, and listen you. So you can start.
Okay. So hello everyone. I'm Guilherme Pucenti, and this is the presentation for the paper Trajectory Detection Method for Transmission Line Path Following Control. So for the introduction, the inspection of power lines is an important task to maintain the quality of the power transmission. A power shortage, for example, could lead to accidents and financial losses. So in the past, this task was performed mostly by mobile vehicles or human operators. But nowadays, most studies employ cameras attached to UAVs. So these are common transmission lines faults. And here are some inspection examples. The first two ones was mainly done by humans. And we can see it's a dangerous task because there's a interaction between the human and the power lines. So this task must be avoided. And one of the solutions is the use of aerial vehicles. And in the third one, we have a mobile robot. And this kind of system has its own limitations because it must avoid the trees in this example. So this kind of system is not desired nowadays. So related works for transmission lines inspection is divided in global versus local planning. For global planning, GPS is used as a global planner to track the power lines which must be followed. So for the local planning, we have cameras and LIDAR sensors, which are employed as a local planner to smooth the path and avoid some obstacles. So this paper aims to propose a trajectory estimation method to transmission line path following problem, which is going to be applied to UAV. The proposed method was employed together with an MPC controller, which aims to determine the control actions to be applied to the UAV to follow the lines. So now we're talking about the problem formulation. These are two representations of our problem. The first one is the lateral view of the problem, where we have a UAV and a camera attached to it. The UAV is at a height h up from the lines, and this point PF, it's the point which we're going to evaluate the errors. So here are the aerial view of our problem, where we have in this case 3 power lines, and the UAV has a lateral error related to the point PF, which is the variable z, and we have a phi, which is the angular error between this vector xr and the vector t, which is tangent to the trajectory. So we have these two variables that must be minimized. So we apply a transformations of velocities from the world frame, which are the 3 variables, and the robot frame, which has these 4 velocities. And this is the matrix to transform these frames. So next, we apply a Serre-Frenet system, which is the equation number 2. And then we can evaluate these 2 equations, Z and S. So next, we define the state errors of our system. And these are the 2 variables stated above, Z and phi. Z is the lateral error, and phi is the angular error. And UOPT is the control action that must be sent to the UAV, that we have R, which is OPT multiplied by cosine of theta. And then we employ R to the UAV to minimize the state errors. Next, we are going to talk about the methodology of our paper. First, we have a raw image from a camera, and then we can apply a grayscale transformation and Gaussian blur to reduce the noise of the image. Then we can apply a Sobel operator to minimize the horizontal lines and enhance the vertical lines that must be detected. And then we apply a canny edge detector to enhance the straight lines. Next, we applied a half transform to detect the lines. And as we can see here, we have a raw image. And in the second one, we have the lines that were detected through the half transform. So as we can see, the half transform detected the power lines accordingly, but it also detected some lines on the asphalt, which is going to be treated because it's not designed for the system. So next, we're going to explain how we detect the trajectory and reduce the effects of these noises. So for this task, we performed the Ransack regressor algorithm, which works that we first choose 2 random points in the data set, and then it regresses. The regressor calculates the straight line that passes through these points, and then evaluates all the points in layers if the point is inside this threshold sigma or outliers if it is outside the threshold. So the algorithm performs multiple tests, and the best test, which is the line with most inliers, is the fitted model. So here we have an example for our tests. Here we have the raw image. The green points is the inliers of the system, in this case. So the yellow ones is the outliers, and here the green line is the trajectory that was detected. So for the controller scheme, we have the NMPC controller, which is we're going to minimize this quadratic equation. And here we have TP and TC, which are the prediction horizon and control horizon. And Xmin, Umin, Xmax, and Umax is the constraints of, for Xe, we have the states constraints, and for U, we have the output constraints. So Q and R and P are positive matrices that deviates the stage costs and the terminal costs. So for the results, first we have some indoor tests. We choose this track, which consists on a set of 3 strings and a 40 angle deviation between them. And the task, the UAV must follow the lines with reduced Z and VR errors. So for this indoor test, 4 setups were performed. Each setup was tested 25 times. For setup number 1 and setup number 3, the UAV starts above the strings with a forward velocity of 0.1 meters per second. And for setup number 2 and setup number 4, the UAV starts 20 centimeters from the central string and with the same velocities, 0.1 and 0.2 meters per second. And we applied some elementary constraints for the states, 15 centimeters for Z and 0.3 radians for VR, and the UOPT was constrained as well, 0.35. So these are the mean squared error and time to complete each task. So as we can see, for both setups, the errors was small, both for Z and for VR as well. And the UOPT was reduced as well. So the UAV could perform the task accordingly. And for the time, as expected, the first 2 ones were performed with 0.1. So with the increase of the speed, we also reduced the time to perform the tasks. And these are the integral absolute error for both setups. And
Guilherme, can you move to the final results, because we are already you already passed the time.
Oh, okay. So here we have some lateral errors, and in both setups, the errors were reduced, and as you can see, there were 0 errors on the final samples. So here the trajectory detection I'll just play a little bit of the video. It is on a real environment without the controller. So as you can see, in most of the frames, the trajectory was detected accordingly. I will pass to the conclusions. So the UAV performed the task according to the imposing constraints. And on the video, the trajectory was estimated well in most of the frames. So for the future, we intend to test different image segmentation methods, such as neural networks, to improve our detection. And we also want to integrate the detection with the controller in a real environment. We only test the detection with the controller on indoor tests. And this is it. Thank you.
Thank you very much, Guilherme. I'm so sorry to ask you to rush your presentation,
That's
but we are
okay.
already in lack of time. Sorry.
Okay,
So,
that's okay.
congratulations. I knew a little bit what you were doing. So, I have some questions that I would like to ask. The first of all is, how can you deal with environment disturbance like illumination and vehicle motion?
So, well, for the indoor tests, we did not dealt with like we just done the test, not we did not test different kinds of illuminations, for example. So for the future on our real environment tests, we must test different kinds of illumination, because we just tested on videos. We did not apply the controller. So for the videos with different kind of illuminations, the algorithm could detect the lines properly, and Ransack could calculate the trajectory. But this we also need to do more tests to ensure that the method works with different kinds of illumination. And it also applies to some disturbance, because on indoor tests we don't have winds, for example. So on those tests, the performance was well executed, but on outside tests we must deal with wind. So we still need to do more tests to verify the performance of our controller on different kind of disturbance.
Okay, thank you very much, Guilherme. I would like to ask more questions, but I will do directly for you, because we don't have so much time, but thank you very much. And now we are going to move to the last paper of the session, that is entitled Performance Evaluation of LoRa and ZigBee Technologies Applied to Finance. The presenter is Leonardo from IME, and the host, can you display the video? Thank you.
Okay, thank you. Hello, everyone. My name is Leonardo Costa Ferreira, and today I will present to you the paper entitled Performance Evaluation of LoRa and ZigBee Technology Applied to Finance. This paper presents preliminary results from my master's research at the graduate program in Systems Computing, held at the Military Institute of Engineering. Every year, the use of UAV is growing in various areas such as security, surveillance, monitoring, agriculture, leisure, and smart city. Within this context, there are a multi-wave network, especially the FANET, Fly Ad Hoc Network, which originates from mobile ad hoc networks that enable multi-hop communication between aircraft and thus increase the range of communication without the need for multiple gateways. However, this network has several challenges, such as security, wave mobility that occur in 3 dimensions, and communication which is the key point of this work. The choice of wireless communication technology to be employed can result in greater or less power consumption, radio propagation range, data bandwidth, and the other points that will affect the expected goals of a FANET. This paper aims to investigate for the sake of implement FANET type network the transfer rate and packet delivery rate of ZigBee and LoRa technology in point-to-point communication, as these radios are similar in data rate, range, and code. Among the survey work, few studies have performed a comparative analysis between radio and the router protocols applied to FANET. The table presents a comparison of the evidence works with the proposed approach, which aims to analyze in multi-mission FANET the practical performance of LoRa and ZigBee radios regarding range, throughput, and consumption of the routing protocol. ZigBee is based on the IEEE 802.15.4 standard, which implements the medium access in the physical layer, while ZigBee is responsible for the up layers. It supports star cluster and mesh topology using the ad hoc protocol. The radio used in the studio has the XB Pro S3B model from Digi. The power level, according to the manufacturer, ranges from 0 to 4. Begin used for purposes of this works the power level 0 with approximation value of plus 7 dBm and the power level 3 of plus 21 dBm. LARS is one of the main technologies used in wide area and low power network. It belongs to the low power wide area network group. LAR operates in the industrial, scientific, and medical frequency band and have the native star topology. However, they can also implement the mesh architecture. The LAR RED42C model radio from the company Radio Engine has used in the studio. This radio is scatter factor that varies from 7 to 12. For the studio, scatter factors 7 and 9 were used, keeping the transmission power similar to the used in the XB radio. As the picture shows, the necessary structure was composed of XB radios, LoRa, USB serial shields, a notebook, external power supplies, and a Raspberry Pi 3 Model B computer, similar to the processing unit employed in UAV. The test was performed at baud rate 9,600 bps, 38,400 bps, and 57,600 bps. The analysis had performance in both point-to-point radios, first in hard in the loop with a distance of 3 meters, and intersequence in the loop, varying the distance from 100 meters to 500 meters in the urban area. The hardware is remained the same, with the exception of replacing the XB radios with LoRa radios. The investigation took place at the different transmission rates and power plate factors defined during the sending of 50 packs of 232 bytes each. Each scenario of sending 50 packs has repeated 5 times with an interval of 8 seconds between each new sending. At the end, the standard deviation and the average in the scenarios has calculated. The monitoring occurred at Radio 0 coordinator, sending packet to Radio 1 router, and received the AC key packet generated at Radio 1. The graph shows the transfer rate result at a transmission rate of 9,600 bps. It's noted that the XB radio in hardware in the loop was more efficient at both powers, achieving a transfer rate approximately 4 times higher than LoRa. In the human the loop experiment, the XB showed no transfer rate beyond 200 meters at power level 0, but at power level 3, the transfer rate up to 300 meters only decreases significantly compared to the previous distance. As for LoRa in hardware in the loop and the human in the loop, it's noted that the rates in both scatter factor and power employed remain very close, having steady and gradual drops with an increase in distance, except for carry factor 7 with power 7, with there is no rate starting 400 meters. The graph shows the comparison of the packet delivery rate at the transmission rate of 9,600 bps. The XB in hardware in the loop is superior to LoRa in both analyzed powers with a packet delivery rate of 100%. As for the human in the loop scenarios, it's hard to notice that the XB in power level 0 stopped delivering packets in 200 meters. However, in power level 3, the packet delivery rate remains at about 100% up to 300 meters. As for LoRa, it's noted that there is a reduction in relation to hardware in the loop, but the packet delivery rate does not occur from 400 meters in power 7 in the split factor 7. This graph shows the time-lapse comparison at the transmission rate of 9,600 bps. At this baud rate, it is noted that data in the human in the loop scenarios at the 7 dBm XB has more efficient than LoRa at the same power, only up to 100 meters. As for XB on power level 3, there has high efficiency compared to LoRa only up to 400 meters. The graph shows the transfer rate result at the transmission rate of 38,400 bps. On the beach, in hardware in the loop, the XB radio has more efficiency than the LoRa radio at both analysis powers. At the both powers, XB maintains a transfer rate nearly 6 times higher than LoRa at split factor 7 and 30 times higher than LoRa at split factor 9. In the human-in-the-loop experiment on the ground, it has noticed that the XP in power level 0 presents almost no height at 200 meters. However, in power level 3, the transfer rates in relation to the result of the prevision distance are similar until 300 meters, decreasing in 400 meters and getting null in 500 meters. As for LoRa in bench and ground, at both powers at this bound heights were maintained at spread factor 7 compared to factor 9. With increased distance, the bound height gradually decreases at both factor and powers. The graph shows the comparison of the packet delivery rate at transmission rate of 38,400 bps. In the hard-in-the-loop, is noted the radio XB at both powers maintain its packet delivery rate at 100%. In human-in-the-loop, it's noticed the XB radio at power level 0 practically stopped delivery packets at 200 meters. However, the packet delivery rate at power level 3 remains 100% until 200 meters, having a slight decrease at 300 meters and a reduce of 64% at 400 meters. Finally, at 500 meters, there is no packet delivery. As for LoRa hard-in-the-loop and human-in-the-loop, it can be seen that in both powers and spread factor there has gradual decrease in PDR with increased distance, but it's noteworthy that high power with factor 7, the delivery rate reaches a plateau of 80%, while in factor 9, the PDR reaches just over 39%. The graphic shows the time-lapse comparison at the transmission rate 38,400 bps. At this baud rate, is noted that the ground scenarios at 7 dBm, the XB was more efficient than LoRa at the same power only up to 100 meters. As for XB in power level 3, there was higher efficiency in relation to LoRa only up 300 meters. At 400 meters, awards LoRa in both powers level outperforms XB. This graph shows the transfer rate results at transmission rate 57,600 bps. On the bench, at 3 meters, it's noted that XB radio in both powers keep its transfer rates about 5 times higher than LoRa in scatter factor 7 in both powers and with transfer rates about 15 times higher than LoRa scatter factor 9. In experiments on human-in-the-loop ground, it was noticed that XB radio in power level 0 has reduction the transfer rate of 35% in 100 meters in relation to bench. As for other distance, the power level 0 has no transfer rate for 200 meters. As for level 3, the transfer rate compared to the previous distance gradually decrease up to 300 meters. After distance, there are sharp drops in the rate to almost zero. In the case of LoRa, it's worth noting that the transfer rate in both scattering factor and the power gradually decreases with increased distance such as 400 meters. Finally, in this baud rate, we can verify the highest rate in the scatter factor 7 with values about 3 times higher than the scatter factor 9. The graph shows the comparison of the packet delivery rate at transmission rate of 57,600 bps. On the bench, it's noted that the XB radio at both powers maintained its delivery rate at 100%. In the human-in-the-loop experiment, it was noted that the XB radio in power level 0 at 100 meters maintained its delivery rate in relation to the bench. At the other distance, XB in power level 0 stopped delivery packet from 200 meters. The PGR in power level 3, compared to the results in previous distance, remains at about 100% until 300 meters, having sharp drops from 400 meters. As for LoRa, the delivery rates decrease gradually with increased distance in both power and spread factor. However, it can be seen that the best rates occurred in high power with factor 7, where the values up to 500 meters were between 92% and 98%. At spread factor 9, this rate reached the maximum level of the little over 39%. This graph shows the time-lapse comparison at the transmission rate of 37,600 bps. At this baud rate, it's noted that the ground scenarios at 7 dBm, the XB was more efficient than LoRa at the same power, only up to 100 meters. As for the XB on power level 3, there as a high efficiency compared to LoRa only up to 300 meters. Therefore, at low power in the scenarios from 100 meters, towards only LoRa could get some packet transfer delivery rate. As for the high power only from 400 meters, towards LoRa managed to outperform XB. We can see that the XB radio is more efficient at the boost bit power, but on the ground at the power level 0, the XB is more efficient only at 100 meters. XB power level 3 is more efficient only 300 meters in all data rates, and all other distance LoRa is superior. Futuro will focus on further ground tests for a synchronous rate and employing funded in real flight using a fleet of quadcopters. We are very grateful to CAPS for the financial support to this research project. These are the bibliographical references used in this work. We thank you for the opportunity and we are at your disposal for any further clarification on this content. Thank you very much for your attention. Hello everyone, my name is Leonardo Costa Ferreira.
Thank you very much, Leonardo. I will start doing the question in English and then translate to Portuguese, okay?
In Portuguese, please. Thank you.
Okay. Is a very nice subject. When you talk about communication, this is a really essential aspect for swarm of UAVs. So when I was reading your work, I was instantaneously thinking regard multiple UAVs. So my question is if you have some undergoing work on real drones. So translating now. Eu achei seu trabalho maravilhoso, muito interessante quando você fala sobre comunicação, né? O primeiro aspecto que eu penso instantaneamente é múltiplos UAVs, porque é muito importante a questão da comunicação e CT Zigbee e LoRa, né? Então, queria saber se você já chegou a fazer algum trabalho considerando drones reais.
Bom, primeiramente, boa tarde. Agradeço aí a tradução da professora. A intenção do trabalho, né, na verdade, isso é parte do trabalho, a intenção do trabalho seria realmente fazer voos reais, né? Então, eu já estou na fase agora de testes em solo, com múltiplos rádios, né, fazendo o trabalho em rede mesh, e a intenção seria realmente conseguir fazer o voo com múltiplos drones e analisar o desempenho.
Então, você já está nesse trabalho já de testar com drones reais?
Eu estou na fase de finalizar os testes de solo, né, em redes ad hoc, né, em redes mesh, para, se der tempo, conseguir realmente realizar os testes com voos reais, né, com os drones.
É bem interessante e depois eu fico guardando os resultados também, para eu poder saber como é que vai funcionar. Parabéns, tá, Leonardo? Eu peço desculpas, mas a gente já está atravessando um pouco a sessão. Bom.
Obrigado, professora. Eu agradeço a todos e agradeço a senhora aí. Obrigado.
So thank you very much for the audience and the authors to present the papers. Now I would like to ask Professor André Marcato to come here and chair the next section. Thank you very much.
Thank you, Milena. Are you hearing me?
Yes.
Yes, okay, thank you. Let's get started. Then, hello everybody. My name is André Marcato and I am full professor of Federal University of Juiz de Fora. I would like to give my welcome words to everyone, so the people in the Zoom room, as the people in the YouTube channel. We are going to kick off the control and the robotic system session. We have here 4 papers. First of all, I would like to invite the presentation author of the paper number 1, surrogates for the assessment of robotic manipulators reliability. I think that the author Fabian Molina are going to present this work. I'm right?
Yes, I prefer to reproduce the video, please. It is possible to?
Yes,
to present the video?
The host can show the video.
Okay, thank you.
Okay, thank you, Fabian.
Hi, I'm going to present the work entitled Surrogates for the assessment of robotic manipulator reliability. My name is Fabian Molina, and this work was done in cooperation with Professor Koroishi and Jacqueline Machida from the Federal University of Technology, Paraná. The robotic manipulators are subject to uncertainty. The main source of uncertainty is the clearances of the joints. These clearances are necessary for the relative motion between the links, and the calibration and the control strategies have been used to minimize the effect of these errors, and therefore it is necessary to develop methods that quantify the effect of these errors. The present contribution presents a comparative study of several methods to assess the kinematic reliability of manipulators by using the probabilistic theory and the fuzzy approach. Our methodology: first, we present a method to compute the total error in the N effector produced by the joint clearances. Then the uncertain parameters of the clearances are modeled as random variables and also as fuzzy variables. And then 4 methods are used to evaluate the reliability. First, we have 3 methods based on the probabilistic approach: the Monte Carlo simulation, the first order reliability method, FORM, the second order reliability method, SORM, and the fuzzy method. Here is the outline of my presentation. The methods will be evaluated in this manipulator, which is a 3 degrees of freedom manipulator with the 3 revolution joints. The DH parameters are present in this table, and in this figure is present the model of the joint clearances. Each clearance introduced 2 additional degrees of freedom, one displacement in the x-axis and another displacement in the y-axis, and the 3 joint clearances introduce 6 different degrees of freedom in the manipulator set in this vector, in the vector lambda. First, the method to propagate the error of the clearances. I'm mapping the joint clearances in the total error of the N effector, as presented in this expression. This expression is based in the M matrix, and the N matrix is a matrix that is based in the homogeneous transformation matrix that takes into account the homogeneous transformation between the frames of the manipulator, and the N matrix, which is a total orientation matrix, and delta E is the screw representation of the joint clearances. Then the uncertain parameters are modeled as random parameters, as a normal random parameters. Therefore, each parameter is defined by the mean and the standard deviation, as presented in this expression. When omega is a normal stochastic process, and then the fuzzy parameters are modeled as a triangular fuzzy variables, as presented in this figure. The kinematic reliability expresses a measure of the position error exceeds the maximum error limit, as presented in figure 3. The operator C represents a measure of probability or a measure of possibility. The first method, we have the Monte Carlo simulation Monte Carlo simulation. This method has 3 stages. In the first stages, the uncertain parameters are sampled. Then the kinematic error is computed for each random input. And finally, the probability of failure is estimated as the rate of the failure samples and the total number of samples. In this way is estimated the probability of failure. Then the first order reliability method, the random variable, the random vector is transformed into a standard normal variable u, and the state limit function is linearized by using the Taylor series, only considering the linear term, and the probability, reliability coefficient beta is estimated by solving this optimization problem. Finally, the probability of failure is estimated by considering the standard normal cumulative distribution as presented in this expression. Then, and the last probability method is the second order reliability method. In this method is considered the state limit function as a nonlinear model. Therefore, the first nonlinear term of the Taylor series of the state limit function is considered, and the probability of failure is estimated by using the expression of equation 6. Finally, the fuzzy method, the error is expressed as intervals weighted by the membership function as equation 7 presents. Therefore, the alpha f, which is the measure of the probability of failure, is estimated by using the me operator that represents the possibility, the possibility of failure. And this estimation of this possibility of failure demands the estimation, the evaluation of the membership function that is a value that is contained between 0 and 1. In this figure is presented a fuzzy error of the end effector, and we observe the two conditions, an acceptable condition and a failure condition when a maximum error, when the fuzzy error exceeds the maximum limit, max. And the alpha f, possibility of failure, is estimated by using this expression. And we can see that this expression demands the solution of the optimization problem of equation 10. When in the numerical results, first, we have the parameters that define the random variables, the uncertain parameters of the joints. Then the fuzzy variables that define the parameters, fuzzy parameters of the joint clearances, and also the geometrical parameters of the manipulator with the length limits and the maximum limits for each of the 3 joints. In the first result, we have the estimation of the error by using the fuzzy method and the probabilistic method. In the fuzzy method, we observe the membership function of the error, pairs in blue by considering the solution, the alpha solution of the alpha optimization for all the values of the membership function. And in red dot, we observe a linear approximation of this membership function, and we observe that the results are quite similar. And then for the random error in the second figure, we observe the histogram of the error and the approximation of the function of density. And we observe that the results also have a great agreement. Then we evaluate the workspace of the manipulator in the XZ plane and in the XY plane. And we are going to evaluate the reliability, the kinematic reliability for 11 different positions as present in these figures. In this table, we can observe the outputs obtained of the probability of failure by using the Monte Carlo simulation form and SORM terms. And we observe an agreement between these three methods. Nevertheless, in some positions, there are some differences, and we can observe that the SORM method correct the differences between the form and the Monte Carlo simulation. The Monte Carlo simulation is our baseline to evaluate the probability of failure. And we observe good results for both methods. Then the probability of failure is evaluated for the workspace, and we observe that the probability of failure increase in the outer border of the workspace. This is obtained because the manipulator is completely extended. And we observe a similar behavior by considering the fuzzy method as presented in this figure. Then we evaluate the computational complexity, and we observe an agreement between the two methods in the computational cost. As a conclusion, we observe that the methods, by using the probabilistic and fuzzy approaches, have good results. The kinematic reliability is a criterion that is used to evaluate the kinematic performance of the manipulator. And as a future work, we will use these methods for the optimal design of the manipulator. Finally, the acknowledgements for the sponsor, the MPQ and CAPES, and thank you for your attention.
Thank you, Fabian, to send this video segment. I would like to open the questions to the audience. Does someone want to ask some questions? I have one question to the Fabian. These results are made by simulations only, or in the real experiments too?
Well, these results are based on numerical simulations. Yeah. Basically, we consider the numerical model, but only considering the kinematic model of the manipulator.
Okay. Are you planning construct a real system to implement these techniques?
Yes, of course. At this time, we are working with flexible robots, and we are evaluating the effects of the uncertainties in the mechanical properties of the flexible robots. I think that is a little bit complicated to evaluate the position errors. I mean the kinematic errors produced by the joints by considering experimental results. But I think that by evaluating the dynamical uncertainties in these flexible roads, we will have excellent experimental results.
Great. And my last question is: are you using a fuzzy classifier? Do you think test with the other classifiers like a deep learning or other technique?
Yeah. Well, the approach that we are using is not a classifier. Is related to a method that maps the fuzzy variables, the parameters of the system model as fuzzy variables in the output of the system. I think that these methods that you mentioned are related to the prognosis of error. I think that by using machine learning, and I think that it's an interesting approach to predict the failure of the manipulator. And I think that is an interesting topic for future work, of course.
Okay, again, congratulations for your presentation.
Thank you so much, Professor.
I desire success in your master degree or PhD degree.
No, this work is for my undergraduate student.
Oh, great, great. Congratulations.
Thank you so much, Professor. Thank you.
Let's move to the second paper. I think that the author, Carlos Ernesto, is here. I'm all right?
Hello. Yes. Good day, everyone.
Okay. Can you present your do you want to share your screen or show the video segment?
Can we show the video, please?
Okay.
The internet is not good here.
Okay.
Thank you. Good day, everyone. I'm Carlos Ernesto Vázquez Garcia, part of the Robotics and Advanced Manufacturing Department at the Research Center for Advanced Studies in Mexico. Today, I'm going to show you the overview of our paper named Quasi-Static Optimal Design of a Pneumatic Soft Robot to Maximize Pressure to Force Transference. This is the table of content of the presentation, and now let me give you some motivation of our work. So, rigid robotics continue to amaze us at record speed due to their incredible precision in tasks like positioning and grasping. However, their limits have also been put inside in applications where compliance and dexterity are needed. Also, due to their high stiffness and inertia, their designs are generally bulky and have high energy consumption. In contrast, soft-body robots have erupted and changed conventional robotic research by mimicking nature when considering deformable, lightweight, and hyperelastic materials. However, there remains unresolved many basic issues arising from their principal property, which is continuum deformation, ranging from kinematics and dynamics to planning, control, and optimization. In this last area, due to the lack of complete models that clarify the intertwined components of soft robots, many optimization problems have been oriented through empirical methods, as it is difficult to identify correctly the optimization variable. So, from here, we notice that the general problem is to obtain a design based on a model to fulfill a requirement. In this project, we address internal pressure chamber design problem, which relates directly to the model-based design of the topology in actuator space. Also, we dealt with a common problem in robotics, which is the design criteria for energy transfer. Therefore, our problem was how to design a soft robot to perform a task with less energy, given a desired configuration and a desired pressure vector. To solve this problem, we first considered the following Lagrangian model, which was submitted as a companion paper at this conference and which presentation will be held after this one. This Lagrangian model for soft robots is seen in equation 1, which is based on D'Alembert's Lagrange equation and in the constant curvature hypothesis, so that we can characterize the deformation of the robot with three variables, which represent our generalized coordinate vectors, and that can be seen in figure 1, which are the length L, the azimuth phi, and the curvature kappa. The generalized force tau deserves special attention, since contrary to the case of typical rigid multivariate Lagrangian models, it is the image of the configuration space from actuator space through an input matrix we call V. This input matrix can be calculated by the partial derivative of the volume of the chambers by the deformation coordinates, as we can see in equation 3. So, for our case study, we consider a robot with three pneumatic chambers distributed at 120 degrees, as we can see in figure 2. Also, these chambers have the same area. Therefore, our input matrix is full rank and has the following form. Notice that the chamber area weights all the elements of the input matrix. Also, it's precise to point that this design that is held in quasi-static regime, so that the model reduces to the one seen in equation 4. Regarding to the solution, For reference, I want to first point that common designs of sub-robots in literature are similar to the one seen in Figure 3a, where each chamber has a circular shape and are distributed by an angle c. Also, its centroid passes a circumference of radius r sub m, so that the bigger this radius is, the greater relation between generalized forces and pressure will be. However, this design is not the best one, because input metrics suggests that the ideal but naive solution arises by enlarging the maximal possible area of the robot's cross-section and only restricted by the wall of the elastomer, as seen in Figure 3b. Here, both the area of the chamber and the radius that crosses chamber centroid is dependent to the external radius, which makes the input matrix to be also dependent to the external radius. As our design objective was to maximize pressure transference to generalized force, the input matrix is an excellent candidate for the optimization problem. We propose the square norm of tau as our preliminary cost function, which for a soft robot take the form of the expression in 5. From here, we notice that given a desired general of force, the norm of the vector of pressure is minimized when B transpose times B is maximized. But as this expression is not a closed form, we need to represent it by a scalar, which in our case was its maximum singular value, also called the spectral norm of B. So our preliminary expression is upper bounded like equation 6. If we plot the singular values of B as in Figure 4, we can see that the spectral norm corresponds to two singular values depending on the deformation coordinates. So, by taking the non-trivial root of the subtraction of singular value 1 and 3, we get our border that we call L thick, which is seen in equation 7. We can now define our optimization problem as maximizing the spectral norm of the input matrix by maximizing the external radius, subject to the model in quasi-static regime and an upper restriction delimited by a maximum radius of the robot. This problem was solved by the extended Lagrangian method, where we subtract to our cost function our active constraint by a Lagrange multiplier as seen in equation 11. From here, we got our optimal external radius, which satisfies the Karushkin-Tucker conditions stated in equation 12. Other geometric variables corresponding to the initial volume of the robot is the initial length, which, as it wasn't included in the input matrix, we needed to add it some way into the model. Here, our parameterization objective is to obtain an initial length such that for a desired configuration of the sub-robot, we require at most a desired vector of pressure. So for that, we modify the elastic forces of the model by approximating it with the elastic potential energy proposed by Goddard, where it is represented by the sum of an energy of extension and an energy of bending. Also, by using the second Castigliano theorem and Hooke's law, our elastic potential energy corresponds to the one stated at equation 13, where A is the chamber area, I sub A is the area moment, and E is the Young modulus. By obtaining the partial derivative of this elastic potential energy with respect to the deformation coordinate, we then obtain an expression for the elastic forces as seen in equation 14. Then, we equal this expression to the one obtained in the quasi-static model as seen in equation 15. Notice that the first and third equation have our design variable, and as the gravity vector also depends on the initial length, we'll have a quadratic equation giving us 4 theoretical solutions of the initial length, but only those with a positive lower bound of the desired length are physically viable. For a case study, we simulated 3 designs of soft robots. The first one that we call Robot RA was taken from Satari's work, Robot RB from Mustasas, and finally Robot RC corresponds to our design. The measures of each robot can be seen here in Figure 5. All 3 robots have the same initial length that corresponds to a desired pressure vector of 1.4, 1.3, and 0.9 psi in the 3 chambers. Also, for a desired configuration of 95 millimeters, 140 degrees, and 5 meters to the minus 1 of curvature. All 3 closed-loop simulations were under a PID control, having the following diagonal matrices for their constants. In figure 6a, we have the resulting graph for the norm of the position error of the three cases, which it has an error around the -3 order, and the same occurs for the velocity errors. Regarding to the norm of torque vector seen in figure 6c, we see that our optimal design requires the most torque, but by analyzing the norm of pressure vector, we see that our optimal robot is the one that requires the least input pressure. In order to compare the behavior of the three robots, we proposed a metric for the pressure to force transference as the norm of tau divided by the norm of p, which, as seen in table 1, our optimal robot is the one that generates the best transference index. For discussions, as seen in results, this model-based design of the cross-sectional area represents an important step in its pressure to force transference maximization. However, previous works have shown through finite element analysis that the ideal morphology addresses a physical phenomenon called Pauling effect, which represents a radial deformation due to pressure force field exerted in the elastomer walls. This phenomenon is not contemplated in the model, as one of the assumptions is that there doesn't exist any radial or circumferential deformation, so it must be contemplated to prevent it. This result is limited to establish the design parameters of a soft robot given a desired configuration and an available pressure vector. However, in order to increase robot's versatility, our methodology should be extended to the case of considering a desired workspace instead of a desired configuration. In conclusion, the optimal design of a pneumatic soft robot is addressed in quasi-static regime to deal with the essential problem of energy efficiency, how to solve a problem using less energy. As a case study, we address the method synthesis for a 3 degrees of freedom pneumatic soft robot based on a novel continuum Lagrangian dynamic model, illustrating the advantages of the optimization procedure for an increase of up to 86-fold of the pressure vector to force transference. Next step is showing the feasibility in practice to study how important are the uncertainties in material characterization, viscoelasticity, state sensing, manufacturing, and power electronics. This may suggest further considerations on what parameters to consider in the optimization, then starting tracking standard of regulation, and finally, the involved dynamic regimen. So this will be all for my part. Thank you for your kind attention, and now we pass to the question and answer section. Thank
Hi, Daniel. Thank you for sending this video segment. Very interesting your work. Are you hearing me?
Yes.
Yes.
Thank you.
Are you speaking from Mexico City?
No, from Colima, Colima
Great.
City. Yeah.
Great.
Yeah.
Congratulations for your work.
Thank you.
Your last phrasing in your last slide is about the feasibility in practice.
Yes.
What kind of the applications for your work? Surgical robots or what kind of applications?
Well, numerics of robots can be applied in or are potentially applied in, for example, minimal invasive surgeries. There's one project named the Step Flop, which was mainly developed to apply it as a laparoscopic device.
Great.
So this kind of solution that we gave can help for the design of a robot to require more a desired vector of pressure. That is that if we want to extend or bend our robot to a desired direction, we need for maximum desired vector of pressure.
Great. And are you very distant of your real robot? Because all results that you presented are obtained with the simulations.
Yes.
Are you planning to build a real soft robot to prove this method and these techniques?
Yes, actually, this was one of my results of my master thesis. The next step was to manufacturing it. So we manufactured this robot and tested at the same desired vector, the same configuration, and we noticed this ballooning effect. That is a radial deformation of the cross-sectional area of the robot. So then we proposed another solution, which was an approximation of the ideal one, which each 120 sector of chamber was approximated by little chambers. For example, well, that circular cross sector was approximated by circular chambers of minus minor radius. I don't know if I explained myself.
Okay, okay, I think that understand.
Okay.
Congratulations for
Thank
your
you,
work.
and thank
Let's
you
move
for
to the
accepting
third
this
paper.
paper.
Okay, let's move to the third paper. I think that the first author, Christian Alexandro, is here. Am I right? I'm right.
Yes, I'm here.
Welcome, Christian. Are you going to share your screen, or do you want that we show the video segment?
Yes, I prefer to play the video, please.
Okay, of course.
Thank you.
Good day everyone, my name is Christian Trejo and I'm a part of the Research Center for Advanced Studies in Mexico. I belong to the Department of Robotics and Advanced Manufacturing and I will talk about the soft cylindrical robots with a work which is a Lagrangian dynamic model for soft cylindrical robots without the internal holonomic constraint. Thank you for your assistance. I hope you enjoy this presentation.
Sorry, I think that the presentation
The content
is
of my
not
presentation
showing.
is the following. I will start with the introduction and
I'd like
Hi,
to.
Christian, did you say something? I couldn't understand you.
Yes, because the video segment of Christian is not running.
No,
I
just...
think okay. I think I played the wrong video. Just a second. Okay.
Okay. Thank you.
Thank you.
I believe it's okay now. Can you confirm, please, Christian?
Yes. I can see the presentation.
Okay,
thank you.
Thanks. Thanks for warning me.
Good day everyone, my name is Christian Trejo and I'm a part of the Research Center for Advanced Studies in Mexico. I belong to the Department of Robotics and Advanced Manufacturing and I will talk about the soft cylindrical robots with a work which is a Lagrangian dynamic model for soft cylindrical robots without the internal holonomic constraint. Thank you for your assistance. I hope you enjoy this presentation. The content of my presentation is the following. I will start with the introduction and I want to define the soft cylindrical robot, which is a continuum body composed of high elastic materials that produce motion through deformation. It is considered as a continuum robot, which implies that it has infinite degrees of freedom and it is actuated by fluids, in this case the pneumatic energy fields. The modeling approaches that we found for the soft cylindrical robot is the finite element approach, beam theory approaches, and energy approaches. Approaches 1 and 2 are accurate, computationally expensive, and use a high number of degrees of freedom. On the other hand, approach 3, compared to 1 and 2, is less accurate, computational efficient, and use a minimal set of degrees of freedom. In control design and stability analysis, it is preferred the qualitative than quantitative models, since control can lead with uncertainties. However, the computational efficiency is important for these purposes. Therefore, approach 3 produce models that are useful to control purposes and stability analysis. However, there is a lack of qualitativeness in models based on approach 3 when modeling deformable robots, which basically is that this model considers the rigid body internal holonomic constraint. That implies that distance between particles is constant. It limits the important effects of deformation, which is the density variation, the variable center of mass, the variable inertia tensor, and the viscoelastic forces. And such consideration impacts not only in the qualitativeness but also in the accuracy. Therefore, the problem is to obtain a Lagrangian model of a subcylindrical robot preserving its deformation properties. Our proposal is to develop the kinematics and dynamics at particle level without considering the rigid body internal holonomic constraint. Our assumptions is that the relative distance between particles is not constant, which is this case for the deformable bodies. Also, we do not consider radial nor circumferential deformation, and axial deformation is constant for the entire column. If we assume that robot is composed by particle columns, the deformation between two particles, or the distance between two particles, will be the same for the entire column but different between the columns. And the backbone line is described by a unique circumferential arc segment, which implies that we are working under the hypothesis of constant curvature. Okay, in the modeling, we consider for the kinematics framework that the robot can be represented by a cylindrical body, and its deformation can be parameterized by deformation coordinate, which is the arc length, the azimuth angle, and the curvature, which is the inverse of the radius of curvature. According to 5, kinematics from inertial frame to any S-frame is this one, and we propose to obtain the particle position with toroidal coordinates, as is the S variable, the C angle, and the radius. And this is the equation for the particle position. In the dynamic framework, we use the D'Alembert-Lagrange formulation, which is this equation where K is the kinetic energy, Q is the generalized forces, and QR are the generalized restriction forces. But for deformable bodies, where the rigid body internal holonomic constraint is not considered, we have that the projection of generalized restriction forces by the admissible motion is not equal to 0. It implies that these forces produce work and needs to be considered into the Lagrangian formulation. Then the dynamic model is developed as follows. We define the kinetic energy as in this equation, where we have the particle velocity, the density, and the differential of volume. Then we propose a density field which is not constant and it's variable and depending on the formation coordinates. We also propose to compute kinetic energy by toroidal coordinates, and the particle velocity is obtained by the time derivative of the last equation that we have for the particle position. Then the kinetic energy results in this equation. Now the inertial forces can be computed as follows. We have the inertia matrix. Also, we have the Coriolis matrix obtained through the Christoffel symbols. And external forces, we have the generalized forces and the gravity vector that involves a variable center of mass. In this image, we can see how the center of mass is out of the backbone line. And we have here how density is changing due to deformation. Then we have the viscoelastic forces, and a possible form of viscoelastic forces is this simplified model, which involves linear elasticity and linear damping. Other nonlinear models are compatible with our formulation, as we shown in a companion paper, which is shown in this same conference. Also, we have the pressure mapping that allows to compute the generalized forces. It is computed by the gradient of the pressure potential energy that involves the chamber's volume and the pressure's chamber. We can express these forces as an input matrix times a pressure's vector, which is shown in this equation. An input matrix can be computed as follows. We consider a subcylindrical robot with 3 pressure input as case study, and the input matrix is not constant, which is contrary to what we see in rigid bodies. This matrix depends on the formation coordinates and subcylindrical robot geometrical parameters, and it is well defined for any value of curvature different from 0. Then our dynamic model of the subcylindrical robot is this one, and preserves the structural properties that we found in the Lagrangian systems. And we can express this system in a static case in a regression form, where we have a elasticity parameters vector and a regressor. Then in the results we have the experimental setup, where we have the soft robot, a camera, and 3 valves to actuate the robot. Then we estimate the deformation of the robot, where curvature is estimated using 3 points over the robot, and arc length is estimated by measure the soft robot perimeter. Then we collect some experimental data, and we made a regression to identify the elasticity parameters of length and curvature. Then we have a comparison between experimental and simulation data for the static case, and using this metric we have these errors. We also work with simulation in open loop, and this simulation is depicted into 3 stages. First, we have the natural tracing stage, where robots start from an initial pose and reach a steady state. Then we induce an spin, which is the second stage, where a step force is applied over the coordinate phi, and finally in the relaxation stage this force is removed and the robot starts to dissipate energy until reach another steady state. We also verify the structural properties, and we measure the geometric parameters and body mass directly from the robot, but the dissipation parameters were proposed. Then discussion on the model. Despite our proposed model introduced deformation properties as density variation and variable looped parameters referring to center of mass and inertia tensor, it does not consider radial and circumferential deformation, which impact significantly in the qualitative behavior of the robot and model accuracy. On the deformation coordinates, we have that model exhibit a singularity for null curvature. However, such parameters facilitate the integration with toroidal coordinates and allow to include the density variation. On the other hand, on the constant curvature approach, we prove that it provides good result, but for free motion. It's probably that for restricted motion, or the inclusion of load and contact forces, the phenomenon of variable curvature will increase significantly, and constant curvature approach will no longer be valid. On the parameter identification, model results fit relatively good with experimental data for the steady state, but model must be validated at dynamic regime, and damping coefficients need to be identified. At the end, we prove that if internal holonomic constraint of rigid body is not considered, Lagrangian model preserves both structural properties and deformation properties. Also, while inertia tensor is not shown in this work, it will impact on an inertial formulation, which is our current work. Viscoelastic forces are oversimplified in our model. However, given the Lagrangian structure, other complex models can be included. Our model can be applied to other robot geometries, but deformation parameterization is not a trivial problem. And while our model is limited to the constant curvature approach, it can be extended to a piecewise constant curvature to approximate the variable curvature. And that's all for me. Thank you for your kind attention.
Thank you for your presentation, Christian. Congratulations for your work. Have we questions from the audience? No? I have only one question, Christian.
Okay.
You show some results using the open loop strategies.
Yes.
Do you use also a closed loop strategy too? If you put a reference and the test if your system go to this reference. Possible. Why do you use only open loop strategies?
Why? Oh, okay. It's because we are working first with the modeling of the robot, but it is intended to apply in closed loop simulation. But at this step, we have only developing the modeling part, and we are just make a kind of validation of the model. Then we are working just with the modeling only and not with the closed loop simulation. But we also looking for that because we are trying to preserve the structural parameters of the Lagrangian system, which are useful to design control and stability analysis. But this is part of our theory work, which this model. But the reason which we start with this work is because we found that the models that we found in literature are developed under the rigid body consideration, where the particles is constant, and we start with a model first, and then we will continue with the control and closed loop simulations or experiments.
Great. Congratulations for you. Thank you for your presentation.
Thank you for your assistance. Nice to meet you, all of you.
Okay, let's move for your last paper. I think that Daniel Oliveira is here.
I'm here.
Okay, probably this work is the advisor of this work is the Professor André Scolari, my colleague. He is here too. But now, Daniel, you can present. You can you do you want share your screen or do you want
play the
that,
video? Play the video.
Okay. Okay.
Hello, my name is Daniel, and today I'll be presenting the paper 6D grasping based on lateral curvatures and geometric primitives. Here we have the structure of the presentation, which follows the same pattern as the paper. First, we are going to the introduction, followed by the object detection and 6D pose estimation. After that, we are going to talk about the grasping algorithm used on this paper, the results, and to end the presentation, the conclusions. Now, the introduction. With the hardware evolution in the Industry 4.0, autonomous tasks has become a must in the industry, mainly on robotics. With the evolution of deep learning, the neural networks like YOLO, SSG, and MaskRCNN could be used to detect objects and segment objects, while some networks like PoseCNN and Dense Fusion could be used not just to detect objects but to estimate its 6D pose. And when it comes to robotic manipulators, we also have some neural networks like GKCNN, where they try to estimate the best place to grasp an object, but with only a 4D pose. On previous work, we used the object detection with SSG and a grasping algorithm based on geometric primitives. While it could work really well in grasping an object inside a 3D printer, where you can't move a lot the robotic manipulator, in an open space where the object could be in any amount of poses, it could be troublesome, resulting in bad graspings or failed grasps. To solve those problems seen in previous work, we propose a new system in this paper. Where it's going to use the RGB image to object segmentation pose estimation. If the object class in the pose, you are going to segment the object in the point cloud. With the object segmented in the point cloud, you are going to estimate the best place to grasp the object. After that, you are going to use the kinematic emotion transformation to send the data to ROS. Where it's going to send the final data to the UR5 to grasp the object. In this work, the neural network segmentation driver 6G object pose estimation was used for object segmentation and 6G pose estimation on RGB image. One of the advantages of this network is that it was trained on two datasets, LineMod and YCB dataset. For this work, we only use the objects from the YCB dataset due to the fact that LineMod does not make available the object textures. And we noted on testing that it's mandatory to have the object textures to be detected. In this slide, we can see the network architecture. It will receive as an input an RGB image, where to go to the encoder and two decoders, where one decoder will do the semantic segmentation and the other will extract key points, resulting in the semantic segmentation of the objects. The encoder usage was Darknet53, the same usage on YOLO v3. After the process of removing the key points, it will extract key points as well from the object 3D model. With the object 3D model key points and RGB key points, it will use PNP as known as point in perspective to estimate the object 6G pose. In the end, it will have an age of close to 40 on the YCB dataset, where age is a metric used to define the pose error. After the semantic segmentation, we face a problem. Our grasping algorithm works on point cloud, while our segmentation is on RGB image. To solve this, first, we are going to take the 3D model of the object and convert to point cloud, while downscaling it. By doing this, you have the object segmented in the point cloud. Since we know the object pose, we can simply rotate and translate it based on the estimated pose. This way, we'll have the object in the point cloud, while keeping the object position and orientation. With the desired object to be grasped, segmented on the point cloud, we are going to consider the gripper height, the object height, and a k number of regions, where the object height can be acquired by getting the y max minus the y minimum, and a k will be a number of regions generated by simply divide the object height by the gripper height. This way, we are going to separate a more complex object like this drill in simpler, smaller regions. After generating the grasping regions, we are going to need to calculate the curvature. To do this first, we are going to need to get the object centroid, and you do this by getting the mean position of each around each axis. After that, calculate the covariance matrix and apply PCA, principal component analysis. With this, we can get the eigenvalues and the eigenvectors. With the eigenvalues, as in equation 6, we can get the curvature. To estimate a region geometric primitive, we are going to use a metric called delta. This delta is the percentage of points where the curvature is less or equal than 0.01. So we can say that a region has a X-field primitive if it's lesser than 10%, a cylinder between 10% and 40%, and it's a box between 40 and 100%. If all the regions have the same geometric primitive and the same width, we can say that the entire object is a geometric primitive. When testing the region generation algorithm, we found a problem. First, consider this clamp. Then, cut it in half and consider the handle and the head separate objects. The way the region generation algorithm works now it will consider that both handles are the same object, while they should be considered as different entities. To solve this, each time we generate a region, we are going to apply a clustering algorithm. This way, each handle will be considered a separate region. The cluster algorithm used was the one already implemented on PCL, Point Cloud Library. After the clustering, we found another problem. While some objects can have orientation as seen by the big box around the object, a region can have a totally different orientation as represented by the smaller box around the handle. To solve this, we apply PCA, Principal Component Analysis, to the region to get its orientation. If its orientation is different from the object orientation, we adjust the grip orientation related to the region if that's the region to be grasped. To select the grasp region, first we are going to check if the object is a geometric primitive. If it is, we are going to grasp the object in the center. If not, we are going to calculate the curvature around the x minimum and the x maximum of each region, and generating a score P, where P can be defined by equation 8. This way, we are going to grasp the object with the lowest score P and that has a width smaller than the gripper width. So we avoid objects that are too big for our gripper. Now the results of the grasp region. The best place to grasp will be shown by the red points on the point cloud. Here we can see a banana and a bleach, where the red region is the most linear place of the object on the laterals. Now we can see a tomato soup can and the clamp. Since the tomato soup can is estimated to be a geometric primitive, a cylinder, it will be grasped by the center, so it won't have a head region. The clamp will be grasped by the handle because it is the most linear part of the object. In the clamp case, both handles will have a similar curvature, so the curvature selected will be the one with the lesser curvature, even if it is closer to 0, the difference. And here we have a drill, a complex object. Since the top of the object is larger than the gripper width, it will be ignored by the algorithm, so only the handle and the lower part will be considered. Since the handle is the most linear part of the drill, the region selected will be the handle. To validate the proposed system, the Weebot simulation was used. Here, we can see the object detection by the network, where we can see some false positives. This happened a lot to the clamp due to the fact that the network was trained for three clamps of different sizes. But still, this was the neural network that we found the least amount of false positives. We can also see the object segmented on the point cloud with the region to grasp. Here we can see the robot manipulator adjusting the grip orientation to match the handle, and then grasping the object. We see that due to the errors in position estimation, it won't grasp exactly where it was marked on the point cloud. Now for this experiment, the arm will grasp the bleach. We can see that first the arm will move to match the object orientation, and then move to its position to grasp. For the final experiment, the arm will grasp this tomato soup can. Like the other case, it will first move to its orientation and then grasp it. Due to position estimation error, it won't grasp exactly by the center as it should. To conclude the presentation, the conclusions. In the paper, we presented a 6G grasp system, where we proposed a grasping algorithm. The proposed grasping algorithm works independent of the neural network, which means it will work with any neural network that estimates pose. We validated the system in a simulation environment, but still lack real-life tests. That will be done for future works. The references using these slides. Questions?
Thank you, Daniel. Very interesting, your work. You put all together in the ROS environment. This is very, very good. I have one question. Let's first have you some question of the audience. I think no question from audience. Okay. I have one or two questions. Do you think? Did you consider some haptic constraints when you grasp the objects? If you put haptic constraints when you grasp the objects, when you close the grasper, do you consider this effect?
No.
No? Okay. I think that is a good idea to the future works. And if you do you want to test in the with a real robot like a U-bot?
Yes.
A real
we have
robot?
the UL5 in laboratory.
But did you try to use this technique in a real robot?
We'll try in the future.
In the future?
Yeah.
Okay. Okay, no more questions. Thank you, Daniel. Congratulations.
Thanks.
Then you can move to the next session. I would like to invite my colleague, Professor Eduardo. Is he here?
Yes, I am here.
Okay, Eduardo. Can you continue with the next session?
Yes, good afternoon. It will be a pleasure. Well, we are on time to a little bit late to start our session. Then I would like to ask if Gabriel Araújo is here. First of all, I would like to present me.
Hello.
I am Eduardo Todd, professor of Federal University of Paraná. The first presenter is Gabriel Araújo. Is Gabriel Araújo here?
Hello, Gabriel Araújo isn't here. He is the first author. I'm the second author. He couldn't come here today, but I'm here to answer the question.
Are you Jorge?
Yes.
Okay. Then this work is a new approach of monocular visual odometry to trajectory estimation within a plantation. Then Jorge Filho will present it. Do you prefer to play a video or to make a live presentation?
I would like to show the video.
Okay, then I ask the host. Thank you.
Hello, my name is Gabriel and I'll be presenting the following paper entitled A New Approach of Monocular Visual Odometry to Trajectory Estimation Within a Plantation. The motivation of this paper is the difficulties that farmers suffer in the agricultural environment, that is, the identification of areas that are hard to access for carrying out activities. There is a constant need to develop new methods for precision farming, need to ensure safety and comfort for farmers to move around in their work environment. The objective of this research is to implement a new approach of monocular visual odometry algorithm to estimate the travel trajectory by a small robot, the Terra Sentia, in an agricultural environment and test the efficacy of the method. The implemented algorithm starts by capturing the first image, k-1, and extracting the features of that image. Then, it captures the next image, k, and extracts the features of that image as well. After that, the algorithm tracks the feature movements between those images and generates an essential matrix. On a standard visual odometer algorithm, the rotation and the translation matrix would be taken from the essential matrix, But our approach only takes the translation matrix from the essential matrix, where the rotation matrix is defined by the purpose method. Once you have the translation and the rotation matrix, the algorithm checks if there are more images to be analyzed. If there are, k and t are incremented, and the algorithm tests if t is bigger than n, which is a project parameter. A new first image is analyzed. Once you have the image, the proposed method starts by treating it, and for that was applied a Gaussian filter, aiming to reduce the noise. This filter can be described as a convolution of the two-dimensional mask generated from predetermined dimensions and a standard deviation. The next step to perform a color treatment where the image was converted from RGB to HSV color system. To binarize the image, we define maximum values of the parameters hue, saturation, and value, empirically, highlighted for the region of interest, the green. After the binarization process, a morphological opening operation was applied to the image to smooth the present contours, facilitating the next steps. This operation consists of two other operations, one for erosion, followed by one of dilatation. Once the image was operated morphologically, an edge detection function, key edge detector, was performed. This function returned only the contours present in the binarized image. The roof transform is responsible for identifying the lines present in the image. This one works by converting each point of the Cartesian space into a sinusoidal space, corresponding to roof space. A straight line in Cartesian space is translated as an intersection of multiple sinusoids in the roof space. Once the lines were identified, the binarized image was analyzed once more, this time with these lines and inversion of tones, and then the contours, the errors, and the centroids were taken using another function from OpenCV. Once the contour is selected, the lowest value point of y-coordinate present in the contour is used together with the middle point of the x-coordinate of the lower edge of the zone of interest to build the direction vector. Once the position vector was defined for the first image, the same algorithm was applied to the next image, and the difference between the angles was used to calculate the rotation matrix. Now, talking about the features detection process, was used a fast detector, which is a corner detector. This detector chooses a point P around a 16-point region on an image and performs the adjacency criterion to verify if the chosen point P is a corner. P is initially adopted as a corner, so the criterion will verify if P is a true corner. This criterion tests if the intensity of brightness of a set N of pixels is brighter than the point P plus a threshold, and darker than the point P minus a threshold. If both conditions are satisfied, P is a true corner. Once the features were identified, was applied a KLT tracker, Kennedy Lucas Tomasi. This tracker works by using the optical flow D to calculate the velocity which a point U in an image I in the time k-1 has moved to a point V in the image I in the time k. The initial point U is extracted and we have to find V in the next image that has an intensity similar to the one in the point U. To find V is necessary to find D that might minimize the residual font epsilon, like described in the equation. The essential matrix E describes the geometric relations between two consecutive images. It can be found by a 5-point algorithm proposed by Niste. The essential matrix can be described in terms of rotation matrix and translation matrix between two consecutive frames. This matrix is an asymmetrical matrix, and the rotation and translation terms can be recovered by a singular value decomposition of E. Now talking about the results, there are some images from the dataset that were ignored during the process by a skipping image algorithm. These images were skipped because of the presence of some plants on the path that occluded the camera vision. These occlusions can cause errors in the implement algorithm, making it necessary to eliminate their influence so the camera could observe the environment properly. Every 5 frames were also redetected to restart the tracking process because of the tracked feature loss problem caused by the optical flow. To evaluate the proposed method, its estimated trajectory was compared to the one given by the standard visual odometer and the ground truth. The ground truth was obtained using GPS, gyroscope, Hall sensors for the wheel's speed as reference. The proposed method and VO trajectories were able to follow the ground truth, although there are some oscillations in the route, because the robot did not follow a perfect straight line. The oscillations made the estimated trajectory deviate from the reference in some parts of the path. Because some zigzag motions were very small, the optic flow did not recognize correctly such motions to estimate the oscillatory behavior. The small difference from the ground truth were caused by the drift problem of the visual odometer, which directly reflects on the proposed method. The proposed method followed the ground truth better than standard visual odometry. The estimated trajectory of the proposed method deviated less from the reference. Errors caused by the drift problem and by Robert's uncertainty oscillations were smaller. The proposed method computed the rotation matrix without target features, which ensures that unfiltered outlines by insect does not interfere in the rotation matrix estimation. The table shown in that slide that the translation mean square errors with respect to ground truth and the average process time of these methods. It's possible to notice that although the method achieved translation error close to each other, the proposed method shows smaller translation errors than the classical visual odometry method. Furthermore, it was obtained that the average processing time of the proposed method is 16.09% longer than the processing time of the standard visual odometry. These was already expected, since the proposed method algorithm runs more processes than the standard visual odometry method. In conclusion, the better performance of the proposed method occurred due to the better estimation of the rotation matrix used to calculate the pose of the robot motion. This matrix did not present interference in its calculation, caused by the presence of points outside the curve, since it was not extracted directly from the computed essential matrix. It's important to emphasize that some planes of corridor can harm the trajectory estimation, so it has to be accounted for some interference that the algorithm suffers. For future work, we will be applying the proposed method on the robot and do a field testing, and also fuse the proposed method with other types of sensors. Finally, I would like to thank the whole team that helped me with the research, the Mobile Robotics Laboratory of University of São Paulo, the São Paulo State's Research Support Foundation, the University of Illinois at Urbana-Champaign, and Earth Science for the support. And you for watching. Goodbye.
Okay, thank you for your presentation. Does anybody have a question? Yes. Who has a question, please? No YouTube questions.
Hi, Todd. I have a question.
Yes, please.
Thank you, Gabriel. Gabriel is not here. Thank you, George, for your work, for your presentation. I have a question. Gabriel said in the presentation that you're having problems with occlusions of the plantations. So how do you plan to deal with this kind of problem? Thank you.
So actually, the best approach is to develop a computer vision algorithm to try to recognize these plants that are falling on the floor, for example. But in this work, to solve this problem, we only skipped some frames manually of the data set that we've used, and we implemented on the algorithm also a process that verify the quantity of inliers that the tracker got to track the features in this case. So this process that we implemented, that if, for example, there is a percentage of inliers less than a number, the frames are skipped in automatic scheme. But this doesn't got to solve all the problems of occlusion, so it was necessary to skip manually in the data set. We were looking at each frame on data set, and we note then and skip it.
Okay, thank you. Well, it was a very nice presentation, very interesting work. Congratulations. I have some questions, but we are on time to the next work. Then I will let them for another opportunity. Okay, thank you for your presentation. Then
thank you everyone.
The next, yes, great. The next work is degradation driving underwater imaging enhancement. I suppose that Claudio Melo will present. Is Claudio Melo here?
Yes, yes. Hi, George.
Okay.
Nice to meet you.
Hi. Yes. Okay, it's your. Do you prefer to present in live session or to play a video?
The video, please.
Okay, host, please, and I will turn my camera off. Thank you.
Hello, my name is Claudio Melo, and I will present the work Degradation-Driven Underwater Image Enhancement. Modern underwater activities such as maintenance, inspection, and marine life exploration are performed based on remotely operated vehicles. In these activities, images and video footages are acquired. The image quality depends on depth, particles in suspension in the water, and ambient light. The depth causes changes in color perception, and the turbidity causes blurring and contrast loss. The ambient light increases the turbidity perception in the image. Often, the acquired images have some distortion due to these factors, requiring improvement of the image quality. In this work, we propose a deep learning single image architecture for underwater image enhancement. Our approach is based on unsupervised learning, and the method requires no paired datasets. The strategy uses the degradation present in the image as information for its removal and for the enhancement task. In an autoencoder, the output image is a reconstructed version of the input image. In the training phase, the input and output images are matched in the loss function. The autoencoder learns to reconstruct an identical version of the input image. In this work, we propose to insert a degradation function that increases the degradation in the output image and produces a degraded version of the output image. This degraded image replaces the output image in the loss function. This procedure misleads the neural network training. The autoencoder learns to compensate the degradation, removing it from the reconstructed image. At the end of training phase, the autoencoder reconstructs an improved version of the input image. The degradation function is the key element in the method. So, how is the degraded image composed? Here we have an input image and the diagram of the method. The degraded image is composed from three images: the output image, a degraded version of the input image, and an improved version of the input image. So we have the degraded image. This procedure is performed during the training phase, and at the end of training we have an output enhanced image. We propose a color space image representation inspired by the underwater image formation model, that is a physical model. In the proposed representation, the parameters are estimated in the RGB color space. This representation is used both in the image processing algorithm and in the loss function. The autoencoder is a lightweight neural network, and it has only 130,000 trainable parameters. The encoder section has two pipelines in order to improve the performance and generalization ability of the network. Each encoder pipeline accesses to the skip connection in a random way, defined by the random switching function. The loss function is described in YUV and HSV color spaces in order to improve the color recovery and color preservation. It is composed by the scene and image components, and all terms are MSE between input and degraded images. The scene components are dedicated to the dehaze action objects, highlighting and color and contrast recovery. The image components are dedicated to the context information, image reconstruction task, and color and contrast recovery as well. Here we have some resulting images from the method. In the upper row we have the input images, in the mid row the degraded images generated by the degradation function. In the lower row the output images are shown. The output images present color and contrast improvement, and there is color cast and haze reduction. Only real images were used in the autoencoder training. And here we have more results. In the same way, the output images present color cast reduction and improvement of the contrast and the color. Also, we performed a comparative study involving similar underwater image improvement methods. Our method presents a good performance related to the other methodologies, with color preservation and contrast recovery. Ending the presentation, I would like to highlight that the input image is the only information needed by the method, without any prior processing. And an unsupervised learning methodology was presented that requires no paired datasets. In future works, we intend to extend the method to assist applications such as underwater monitoring and inspection. Thanks for watching.
Okay, Claudio, thank you for the presentation. Does anybody have a question? I have one. Do you know or use it some metric to evaluate the image enhancement? For example, you can see that your method seems to be better than the others, but is there any metric to measure that?
Yes, we used USIC and UKEM metrics to evaluate these images. Both metrics are to underwater images, and they are no reference metrics. Our method performed good results in these metrics.
Okay. And what about the illumination changes? Not just distortion due to the water, but also due to illumination change. How does it behave with the training? If you train it in the morning, for example, and then you have images taken in the afternoon, how does the method behave?
Can you repeat, please?
Yes, my question is about how your method behaves when you have illumination changes also added to the water distortion.
Okay, the image provides all information that we used in the method. Then the illumination present in the image are tackled by the method directly. We do not use a specific treatment for the illumination, and we have in the image representation in the color space, we use context illumination to represent the ambient light.
Okay, I know that. Okay, thank you very much. We have 1 minute for another question. No? If no, then thank you for the presentation, Claudio. And then I will call the next presenter. Thank you very much. The next work is pedestrian trajectory prediction with pose representation and latent space variables. Anderson Santos and Valdir Grassi Jr. Who presents that?
Hi, Eduardo. I'm going to present the paper, but Anderson is also present to answer questions.
Okay. Will you present in GIF session, or do you want to play the video?
I will share the slides. I hope I can.
Okay, great. Then you can begin. Thank you very much.
Thank you. Eduardo, I guess I will. I have to just unlock this.
No problem. Take your time.
Just a minute. Okay. Is it all right?
We see you.
Okay.
Yes.
Sorry for the delay. Okay, I'm going to present the paper Pedestrian Trajectory Prediction with Pose Representation and Latent Space Variables. I'm Valdir Grassi Jr. from University of São Paulo. This is the work of Anderson Carlos dos Santos. Okay, so the motivation for this work is in autonomous vehicles. Autonomous vehicles has the potential to improve safety in urban environments, urban traffic, avoid collisions, accidents. It can also bring comfort to passengers and also has the potential to traffic optimization. In this video, you see the Waymo's car, how Waymo's cars see the environment. So you see the pedestrians being detected, other cars, also traffic lights, etc. So it's important in this context to detect the pedestrian intention, so that the car may avoid accidents if he sees a pedestrian intending to cross the street. So a pedestrian trajectory prediction is an important perception task in this context. In this work, we developed an architecture for this perception task for pedestrian trajectory prediction that is based on LSTM, long short-term memory, pedestrian's position, sorry about the spelling here, pedestrian's pose, vehicle speed, and also the temporal latent space. In this work, we use the PI data set, pedestrian intention estimation, that is a data set collected on the streets of Toronto, 6 hours of driving in Toronto, Canada. Our approach uses, instead of using only pedestrian's position in bounding box, or using image crop of the pedestrians in the image, we use the pose representation. So in our approach, we use the open pose framework to extract 25 key points from the pedestrian. These 25 key points represent the pedestrian's pose. Open pose is able to give those 25 points, also connect those points. It also gives a confidence level of a point being part of each body part, but it cannot automatically detect instances. So in our work for tracking the pedestrian and to track each instance of the pedestrian, we have used the annotated data from the data set. So in this work, we did not dealt with the tracking problem. We only dealt with the pedestrian trajectory estimation. So after representing the pose, we also use the latent space variables we learn from the sequence, the movement sequence, the latent space, and we are assuming that this latent space has information that is helpful for predicting the future positions of the pedestrian. So here we train an LSTM autoencoder. So in the pre-training phase, we enter with a sequence of here is only the center pose of the pedestrian. Here we enter with a sequence. We train also a decoder with that returns another sequence. But then when using our framework, we only use the encoder part, and then we use the latent space together with the external features, that is the position features, and to forecast. So this is an overview of the entire framework. So from the image sequence, we extract pose, we create a structured data composed of a sequence of pose. We also learn the latent space, the spatial latent space. In this case, we have the 25 key points from the pose, and then the output is only 8 points. That is the latent. We reduce the space from the 25 key points to 8 points. Also, we have a temporal encoder that extracts the latent space from this temporal sequence, and then we also use the vehicle speed sequence as input to the framework. So the framework receives the temporal latent space, the sequence of positions, pedestrian position. It receives the latent space of the spatial encoder and also vehicle speed. And then we train a network composed of bidirectional LSTM, attention mechanism, and LSTM decoders to forecast the pedestrian trajectory. So we compared this whole framework with simplified versions that only use part of the information, and then our results show that when we use all of this information, we get better results. This framework is less complex or has less parameters than other frameworks that use convolutional LSTM, and so by extracting the pose of the pedestrians, we reduce the complexity of this framework, of these solutions. We also we compare this framework using the data automatically extract from the open pose, and we compared with the annotated information from the data set. So also here we have a video showing the trajectory prediction for the 1.5 seconds ahead. By the way, we use 0.5 seconds to forecast 1.5 seconds. Here is an image showing an example of the results we get. The green, the red dot is the ground truth. The yellow is the prediction with the full model, and the white and purple are when some of the informations are left apart. Here you see that the horizontal prediction is quite accurate, but we have a large error on the Y on the Y position, Y-axis position. So, but here in this example, for example, the most important information is the X position forecast. Here we compare training with label data, annotated data from the data set, and also training only using the points extracted, automatically extracted by OpenPose. So in the case we don't have annotated data, we could use OpenPose to extract automatically the key points, use the center of the pose as the position for the pedestrian, and also train the network with this information. In our case, all the testing data is done with the annotated data, but the input for the network could be either annotated data or automatically extracted data. Here is a slide showing our results compared to others, results in literature. Here is the PI, the work of Razuli that proposed the PI dataset. We see that our result does not achieve the state-of-the-art result, but it's not quite that far as well. But we can see that compared to the baseline that uses only the position of the pedestrian, when we add the latent space and the pose representation, we could reduce the error in 7.6%. Here is other works also compare with their own baselines, and they could get a similar reduction in their proposed approach. So to sum up, the advantage of our proposed network is that we use the pose representation instead of bounding box, assuming that we have more information about the pedestrian movement using the pose instead of only using their positions. We also verified that the latent space could improve the results. The architecture is less complex in number of parameters if compared with convolution LSTM that uses crop of images to predict trajectories. But in this work, we do not handle tracking. We also only estimate the trajectory in the image space, not in 3D. And we observed high errors when we do not use the annotated information for the input of the network. Only when we only use the automatically extracted. But this could be also an advantage. Well, when you don't have annotated data, you can extract this data using OpenPose. For future work, we intended to use tracking to deal with the tracking problem, also occlusion and predicting in 3D. 3D space. These are some of the reference. We thank you for your attention.
Algir, thank you for your presentation. We have time for 1 or 2 questions. Does anybody have a question? No YouTube question. I have a question. How your system behaves in crowded environments?
That's a good
because
question.
it's sometimes one pedestrian comes from the right to the left and the other from the left to the right and then cross. And how did you perform some experiments in this situation?
Maybe Anderson could comment on that, but I don't think we handled that crowded scenarios yet, right, Anderson?
Yeah, we didn't test in this scenario because the problem with the tracking. Because to solve this one, we have
it's
to track
hard, yeah.
And so you see which pedestrians are then. So we did not test this.
Yeah, we have we try to deal in this work only with cases that doesn't have occlusions. So we are not handling occlusion in this work.
Okay, but anyway, you have very
in the
interesting
future.
results. Congratulations. Yes, very interesting work. Thank you.
Thank you, Todd.
Thank you for your presentation. I remember that for all works here presented, everybody is invited to follow the discussion in our Discord channel of our session, and we have a Discord server for the conference or the LARS. You can find the invitation link in our page. The next work is Spark in the Dark, evaluation encoder-decoder pairs for COVID-19 CT semantic segmentation. Bruno Krinsky will present it. Welcome, Bruno.
Hi, Professor. You presented the video.
Okay, host, please, the video of Bruno.
Hi, my name is Bruno Alexandre Krinsky, and I made this work in collaboration with Daniel Ruiz, and our advisor is the Professor Eduardo Todd. Our paper is called Spark in the Dark, Evaluating Encoder-Decoder Pairs for COVID-19 CT Semantic Segmentation. This presentation is divided into introduction, methodology, experiments and results, and conclusion and future works. In this article, we approach the COVID-19 computer tomography semantic segmentation problem. This problem consists in performing the per-pixel classification of COVID-19 lesions into these slices of computer tomographies of patients infected with COVID-19. The objective of our work was to perform an extensive benchmark of segmentation networks and datasets in this problem. Most of the works proposed in this problem based their networks in units and were limited to 1 or 2 datasets. So we noted the necessity of performing a comparison of other segmentation models and evaluating them in more datasets. To achieve our goal, we used the encoder-decoder structure, where the encoder is a standard convolutional network, and the decoder is the segmentation model. We evaluated 20 encoder models. Between them, the most used in the field are HisNets and DenseNets. And we evaluated 6 decoder models, with the units being the models most applied to the problem. We evaluated the segmentation models in 5 datasets: COVID China, MedSeg, MosMed, Record, and Zenodo. The first dataset is the smallest one, with 750 images, and containing 4 classes: background, long field, ground glass opacity, and consolidation. The second dataset, called MedSeg, is also a small dataset with just 929 images and containing 4 classes: background, ground glass opacity, consolidation, and pleural effusion. This dataset presents some issues like coarse segmentation masks and trash markings like circles and arrows, pointing to the lesion regions. However, as the first dataset proposed, it is one of the most used in the studies of COVID-19 segmentation. The third dataset, called MOSMED, has 2049 images and has 2 classes: background and ground glass opacity consolidation. This dataset is very imbalanced, with the lesion regions representing less than 1% of the pixel in the images. The fourth dataset, called Record-1A, is the largest dataset with 9,166 images and has 2 classes: background and infections. The last dataset, called Zenodo, is an evolution of the MedSeg. It contains 3,520 images and has 4 classes: background, left lung, right lung, and infections. Also, this dataset does not present the problems of the MedSeg. In order to evaluate the models, we combined the 20 encoders with the 6 decoders, resulting in 120 models evaluated. We split the datasets into 8% for training and 20% for tests. We used a 5-fold cross-validation strategy to train our models in each dataset, resulting in 3,000 experiments. We use transfer learning with the weights of networks being initialized with the image net weights, and we didn't apply any data augmentation. The images was resized to 256 for 256 to fit the network's input, and we trained the models for 50 epochs and used the learning rate of 0.001, with the learning rate being divided to 10 every 10 epochs. In order to evaluate the models, we used the F-score and intersection of union metrics and used the 1 minus the average of these two metrics as the loss to train the networks. Here we have the training and validation curves for the first dataset. Each line is the average F-score curve of all encoders combined with the decoder. In this first dataset, with exception of the PSPNet and the FPN, all decoders achieved close results. Also, with exception of this dataset, all networks achieve close training and validation curves, showing a great generalization capacity. In this second dataset, the networks achieve very low results when compared with other datasets. This happened due to the coarse segmentation masks and trash markings present in the images. In this third dataset, the highlights goes to the FPN network, which wasn't capable of learning the lesion class. In general, all datasets are extremely unbalanced, with the lesion class representing a small portion of the images. And this dataset presented the worst class imbalancing, with the lesion pixel representing less than 1% of the image. Due to this problem, the FPN network wasn't capable of learning the lesion class. In the fourth dataset, with exception of the FPN, all models achieve very good results. This dataset is the largest dataset in number of images, which help the network's learning process. The network also achieved good results in the last dataset, with exception of the FPN and the PSPNet. We also performed an evaluation of all encoder-decoder combinations in the test set. However, in general, all networks achieved similar results with the validation, so due to space in the presentation, I will present just the results of UNet++, which outperformed the other decodes. The test results for all other decoders are presented in the paper. The blue color results are the best F-score achieved, and the red color are the best interception over union results. Here it's possible to visualize the difference between the encoders, and in general they achieve very close results, which means the depth of the encoder does make much difference, since small encoders achieve similar results with the deepest encoders. Here we present a table with the number of parameters of each encoder in millions of parameters. As presented before, small networks like RegNets achieve close results with the deepest encoders. This is an important result since small network uses a small amount of memory to execute and use less time in the training step. As conclusion of our work, there is no definitive answer which encoder-decoder combination is the best. However, our study provides a guideline for selection of encoder and decoders depending on the scenario in which these networks will be applied. Also, the UNet and UNet++ outperformed the other decoders. However, the LinkNet and MANET also achieve impressive results. Meanwhile, the FPN and the PSPNet show not to be good choice for this problem. For future works, we intend to investigate data augmentation and other balancing techniques, since it showed to be the most critical problem presented in our experiments. The code used for this work is available in our GitHub. Thanks for your attention.
Well, Bruno, thank you for your presentation. Do we have questions? Well, I don't have questions, but I would like to ask you about your recommendation. You did an impressive work. As I remember, you have about 60 pairs of encoder-decoder, something like that.
Yeah.
It's an impressive amount of work. And you wrote in your conclusion some aspects, but what is your recommendation for one who wants to use encoder-decoder for this application?
Well, and I used this study for the next steps of my work, and I used the RegNet architecture because they are small and use less training time and less memory, and achieved close results with other deepest encoders. And for decoders, the UNet or UNet++ is also the best decoders, and probably is the why they are most used in the literature.
Okay, thank you. Another question? No? Then thank you, Bruno, for your presentation.
Thank you, Professor.
I will call the next one is a framework for underwater vehicle localization based on cross-view and cross-domain acoustic and aerial images. Who will present it?
Hi, Eduardo. So I will be presenting. I'm Mateus.
Great, Mateus. Will you make a live presentation, or do you want to play a video?
I will try to do a live presentation.
Good, very good. Okay, then it's your time. You can start.
Okay. I'm a PhD student at Federal University of Rio Grande, and I will be presenting a framework for underwater vehicle localization based on cross-view and cross-domain acoustic and aerial images. So localization is a key features for unmanned vehicle. Let's say we have autonomous underwater vehicle represented by the yellow triangle, and it must follow it's performing surveillance in the marine of this satellite image. So the vehicle must follow the path in red, and the navigation system must know where the vehicle is each single instant of the tasks. So the localization is really important for these tasks. However, the underwater localization is not a trivial problem because of the reduced perception capability of the underwater sensors. For example, the light-based sensors are limited by the water turbidity as shown in these figures. You cannot use this kind of image on this environment because you cannot extract any features. As well, electromagnetic sensors such as GPS does not work underwater. It's limited to only on surface water. However, the acoustic sensors are efficient on the water. As you can see in this image, we are bringing here a forward-looking sonar image captured in the same marine of the previous slide. And you can, this image cover 50 meters in front of the vehicle and 130 degrees. And the white pixels in this image represent the structures that you can see in the aerial image. So you can see the structures in the image and detect it. Here, for a better understanding, we are highlighting the field of view of the sensor and also the features in both the aerial and the underwater acoustic image. So nowadays, satellite images and aerial images from drones are of easy access and provide a rich information of the environment. So here you have in the top image are satellite images publicly available on Google Earth, and the bottom image are images captured from drones. Both images are pretty similar, and usually images from drones have a higher resolution. So based on these facts, we propose an underwater localization method for partial structured environment based on cross-view and cross-domain images. We match the shared features between the aerial and the acoustic image in order to estimate the vehicle localization. It's a cross-view problem because we have the top view of the scene in the aerial image, and we have a frontal view of the same scene in the underwater image. And it's also a cross-domain problem because we have underwater sensor, acoustic image, that's a grayscale image, and we have a colored image that's optical image. So we have two domains. This localization method can be applied in tasks such as inspection, surveillance, object search, and localization. And it allows to perform a navigation guided by the aerial image. You can set a path on the aerial image, and the vehicle can follow this path on the water. We also can apply this method in hybrid vehicles that are drones that can fly and dive at the same time. So this diagram represents our method. It has 3 processing nodes that come from the implementation in ROS. So we have 3 nodes. One node runs offline. First, we do a semantic segmentation of the aerial image, and this image is loaded in the vehicle memory before the mission. We also have the localization node that implements a standard particle filter algorithm and estimates the vehicle position. And we have the matching node that implements the observation model of the particle filter. So this matching node runs a neural network and also runs in a GPU. So the aerial image segmentation, we segment the image in 3 classes: the movable objects in red, stationary objects in green, and the water in blue. So the movable objects are not reliable for the localization because it's moving all the time. So we want the stationary structures that are stationary in the same, so we can use it for the localization. So we extract it in the semantic segmentation. The localization node implement the standard particle filter. All the knowledge of the algorithm comes from the satellite image. And this node behavior to three events. One is the acoustic image, when a new acoustic image is captured by the vehicle. The control signal of the vehicle, the control signal of the motors of the vehicle, and also the image rank event. That's when image coming from the matching node. Also, this node estimates the localization of the vehicle, its XY position, and the vehicle heading. So first, the acoustic image event. It happens every time when a new acoustic image arrives, and it's crop the satellite image regarding the particles of the particle filter algorithm. So we spread the particles in the map, that is the satellite image, and then we crop this image regarding the field of view of the sonar. So basically, we do a lot of crops, one crop for each particle, in the same format, in the same shape of the acoustic image. And then we send this image to the matching node that do the comparison and return the similarity score between the acoustic image and the satellite images. For a better understanding, here we bring the representation. So we have a few particles in the map, and then these particles are transformed in crops, in small crops of the satellite image. And these crops are then compared with the acoustic image in the matching node. So the control signal events in the localization node, basically we are applying a constant velocity model. So we are using the displacement of the vehicle to move the particles in the particle filter algorithm based on the control signal of the model. And the image rank event, it happens when the matching node finishes the comparison, and then we update the particle weights based on this similarity score. And then we estimate the localization of the vehicle based on the better particles. And then we resample these particles using the circle of the fittest principle that kills the particles who have the lower weights and create new particles close to the ones who have the higher weights. So it's the resampling step. The matching node adopt the quadruplet network. This network was published last year on LARS, and basically it's use triplets loss to training two encoders. This network have individual encoders for the aero image and one individual encoder for the acoustic image. This encoder transforms the image in a feature vector of 6-4 dimensions, and then we use the Euclidean distance to find the similarity score. So the method was evaluated using a real data set. In this data set, we have a remote operated vehicle, LBV 300 from Ciabots. This vehicle have a forward-looking sonar, Blueview P900. It's travel for 485 meters at maximum speed of 0.6 meters per second. We also have a DGPS, a differential global position system, who provides us the ground truth of the localization. The sensor is attached on a floating board, and it's follow the vehicle on surface during the mission. Okay. So here we have some results. In this window, we have the field of view of each particle. Here we have the acoustic image that's being processed. We have a few plots that show the vehicle path and the error. Basically here, the localization error of our method is represented by red, and the localization error of the dead hackney is represented by blue. And we also have the map here and the position of the particles that are represented by the purple polygons. The yellow polygon is the ground truth position, the green polygon is the dead hackney, and black polygon is the estimation of our method. So I will quick play here the video. At the beginning, we have a higher error because we started the algorithm with a really high standard deviation. But as soon as the vehicle get close to the structures, the pier, we relocalize the vehicle and we can estimate a better localization than the dead reckoning. Okay. So this is the final results. We show that our method improved the vehicle localization using the aerial and the acoustic image. We decrease the accumulated error of the dead reckoning by relocalizing the vehicle over the time when it's close to the structures in the marine. So, yeah. So in conclusion, we achieve a better results than the dead reckoning using a real data set. And for further works, we are planning to improve the particle filter implementation. Now we are using a fixed number of particles in this simulation. In this experiment, we run 120 particles, but we are planning to use the adaptive Monte Carlo solution that we can change the number of particles depending on the confidence in the localization system. We also planning to do a comparison with different observation model, such as the likelihood field range that's typically implemented in the terrestrial localization with LARS, laser sensor, laser scanning sensors. So yeah, that's my presentation, and thank you for watching. And yeah, I'm open for questions. Thank you.
Well, congratulations for your presentation. I like it a lot, your work. Let me see if we have some questions from the audience. It was very interesting to see it's like a sensor fusion, but in another way that we are used to see in robotics, because you have this 90 degrees difference between the observations. As I understood, your method is more appropriate for near coast navigation because the structures match the underwater. If I am seeing a coral, for example, you don't see from aerial image. Could you comment something about that?
Yeah, exactly. Yeah, this method was designed for partial structure environment. So we need these structures. We need to see these structures in the aerial image, so the method doesn't work. And of course, if you are in the open ocean, the method is not going to work. So yeah, this is a limitation of our method. But we still can apply
it's
this
not a limitation, it's a specification. It's done for this kind of thing. Yeah, okay. I am optimistic. It's not a limitation, it's a characteristic.
Yeah, you're right.
Okay, congratulations. Very nice work.
Thank you, Eduardo.
Well, if we don't have more questions, then we finish the session and we finish the technical sessions of LARS SBR for today. Thank you very much for coming, and see you tomorrow. Don't miss the keynote speak from tomorrow. It would be very interesting from Professor Dilman from Karlsruhe. Okay, and okay, thank you very much. Bye.